everyone. Welcome to another iteration of Math Research Live with me, Charlotte Aten. So today I've got some pretty cool stuff for us to take a look at. My goal, whether or not I actually achieve it remains to be seen, but my goal is to work on some slides for a talk that I'm giving in a couple days at a conference. And so I will be checking those out. And while I'm doing that, I'm actually going to also be trying out a new LaTeX editor on a different platform. If you remember last time, I was saying that I've been using Overleaf for a while, and I like it, but I do also have some complaints. Well, this time around, I'm trying out a new LaTeX situation that should be pretty cool. I've just tried it a little bit so far, so we're going to see how it does me for the rest of the time. But as always, I'm not going to just lecture at you or just bore ahead and do whatever. If you have questions, comments, anything that you want to know or talk about, just let me know. I will otherwise just be working on my stuff, keeping an eye on the chat, and just kind of keeping up a general atmosphere of math things happening. So just let me know if there's anything that you're thinking of or anything that you want to know more about. I'm happy to talk about stuff that came up last time too. So, if you're curious about any of that, like maybe you were here last time or you saw a video, just let me know. Oh, I see that we have someone trying to understand the paper better. You're welcome to ask questions, or just feel free to just post a question in the chat if I start doing something and you want to know about it. I'll otherwise just dive right in and start computing stuff and seeing what's going on. Okay, so with that in mind, let's switch over to my working monitor here, since that's what people are probably here to see, in addition to me myself. Okay, so maybe first of all, here I have a CoCalc project. So CoCalc is it's not just for LaTeX. It's an online platform that I actually originally started using it because basically it's like Google Colab, but Google Colab doesn't support Sage Math, which is like an open source, like a free open source alternative to like Sage, Maple, Mathematica, those kind of like computer algebra systems that can do things like find a basis for a certain vector space, or compute the eigenvectors of a matrix, or symbolically differentiate or integrate a function, or that type of thing. So there's this open source alternative to those, and I wanted something that I could use collaboratively online, kind of like Google Colab, but that would do Sage. And so that's originally, to my understanding, what CoCalc was actually for. But someone pointed out to me when I kind of was complaining about, Sage a little bit on Mastodon, and someone said, "Oh, you can actually use CoCalc to collaboratively work on LaTeX documents like Overleaf." And so I kind of thought, well, maybe it really isn't going to be that great, because like Overleaf even like took a while, and there's a bunch of money and development presumably that went into it, and I don't know, I just, for whatever reason, my expectations weren't quite as high. CoCalc is maybe a little bit of a smaller project, and so while it does work well for LaTeX, it's cheaper, but it's maybe slightly more limited computational resources. You do get what you pay for, though, so you can pay for a stronger computer to be running in the cloud for you. But I was very pleased, just on a basic license, which is much cheaper than Overleaf, actually, for CoCalc, I was able to actually get a pretty good LaTeX situation going on here. And so I've started making these slides for this conference that I'm going to be at. I'm actually hosting one of the sessions at the conference at Iowa State University in a couple days. And so I So I've started making my slides on here, and it's actually coming out pretty well. Like, I really was able to pretty much just do everything like I would expect with either Overleaf or with my local LaTeX installation, and it's looking good. In addition to that, I actually really like the interface as well. I've been having like really positive, just a really positive experience with this interface. I don't know how to do certain things yet. Like, I'm not sure how to use the dictionary that's built into it. So like I'm not sure yet how to tell it that semi-group is a word, for instance. But it's working great, and I'm really excited about it. So if it continues to work well, I'll wrap up what projects I have on Overleaf, but if this continues to go well, and I have good results with experimenting with collaborating on projects over CoCalc, I think I'm going to switch over from Overleaf, because Overleaf is like $150 or $200 a year or something like that, and CoCalc for like the similar functionality, I'm feeling like CoCalc is about $50 a year right now. So it's significantly cheaper, and instead of being something closed source, when you're paying for CoCalc, you're supporting, it's people who develop Sage. It's an open source, it's an open source computer algebra system. Like, all of this stuff, to my understanding, is significantly more free and open source, and you're really just paying for those computing resources. So I'm really hopeful that this is going to be both a better looking and also cheaper and also more ethical solution to this problem of collaborating online with LaTeX. So I'm pretty hopeful. So basically this talk has to do with a calculation, which I'll maybe start to reproduce for you live. I have already started to do some of it, but it's a little bit abstract to explain like where it all came from, so maybe I'll just start actually trying to do some of the calculation, and we'll see if we can see what's going on there. And again, just feel free to ask me questions if anything comes up, or you just think of something that you're curious about. But so I'll just talk myself through where I was in computing this thing before. I do actually have this written down somewhere, but I need to remember how I did this before so I can give a talk about it and be fluent. So it's good for me to just redo it again and refigure it out again. Let's see. Well, what was the first thing I had said? It was that, suppose that we have some binary operation on a set, and suppose that it's associative. In other words, that these two things are equal to each other. So, I don't want x there, I want y. So, in other words, although this notation is maybe slightly less familiar, this is basically the law that multiplication for like familiar types of numbers satisfies, where it doesn't really matter how you put the parentheses, as x times y times z is the same thing as x times y times z. So, if we have some set A with some binary operation that satisfies this law, we say that that's a semi-group, or it's an associative magma. But semi-group is maybe the more familiar term. So many familiar things satisfy this property, multiplying numbers together, multiplying matrices, all sorts of other familiar things, composing functions, and so on and so forth. So the idea was, well, what if we made a linear version of this, or a multilinear version of this? In other words, what if I think about my set A as consisting of some little a1 through some little a_m, however many of them there are. Maybe even to make it a little bit more concrete, I'll say maybe I'll just do maybe three. I'll do three of them. But maybe there's three things in A1, A2, A3, and then I might say, well, this F gives me a notion of how to somehow multiply these things together. And again, if you want more detail on anything, you have a question, or you want like a more detailed example, I'm happy to do that. I'm I'm not under too much time pressure here because I can always finish this tomorrow night before I actually have to give the talk. But I do hope to maybe do some of it, actually successfully make progress on some of it tonight. But if people have questions or just want to see more detailed examples, then I'm happy to do that. I know that we're all, we all have different backgrounds and different levels of abstraction that we're okay with. So, if you have questions, don't be afraid to speak up. It's not like, it's not like I know that we all have the same background. It'd be a little bit different if this was like a class where I knew everyone had taken the same other classes beforehand, but we all have different places that we're coming from, so, I can't assume that you have any particular knowledge, but yeah. So yeah, just again, feel free, if you have any questions or comments, just post them in the chat, and yeah, that should be good. But maybe I'll be slightly more concrete and just do three elements in my set for now. So let's take a look at this. Well, I could say, maybe if I combine A1 and A2, I'd have to say, in order to define a function like this, it basically amounts to choosing a multiplication table, like here's A1, A2, and A3, and maybe, A1 times A2, maybe that's A3, and I could choose, values for all the other entries in this multiplication table for these three things. And depending on how I choose it, this multiplication table may or may not give me something associative. So for instance, I'll leave it to you to check this, but for instance, if I defined it, if I defined it like this, maybe I said A1 and A2 is A3, A1 and A3 is maybe A1 again. Let's see, maybe A1 and A1 is A2, A2 and A2 is A1, A2, A3, A2, A1, and maybe this is also A3. So if I'm not mistaken, this one, for instance, would have this property. I'll just choose an arbitrary triple to check it on, and then I'll leave it to you to check all the other possibilities if you don't believe me. Like if I do A1 times A2, and then I do that times A3, well, in this case, then I would get, let's see, A1 times A2 is A3, and then times A3 would be A3. But on the other hand, if I do A1 and then A2 and A3, A2 and A3 gives me A2, and then A1 and A2 gives me A3. And those are the same. Okay. So at least that, for this triple associates. So in general, the rows and columns do not have to be permutations of A. Thanks for the question. That's a good question. The reason that these ones happen to be is because I actually chose this to be a familiar algebraic structure that I knew was associative. Namely, this is the multiplication table for what is called the group. This is the group of order 3, and it turns out there's only one group. There's only one algebraic structure that's called a group that has 3 elements, and it's this. So I chose this one to be very nice, and all of the rows and columns are permutations of the elements. But I can show you another semigroup that where that's not the case. Here's a very lazy example where it's not a group anymore, it's just some other kind of semigroup. And the rows and the columns are not all permutations of the same list of elements. It's not just a permutation of the rows and columns will not just all be permutations of the set, A1, A2, A3. So one way to do this is I can just define this by setting, let's see here, expand. All right, there we go. So if I just set this to be let's say if I multiply any two things together, any two different things, I just get A1. It's just always A1. That's the only thing I get when I multiply everything together. Well, then if you check any triple, like these ones are probably just any one that you choose. If I do A1 times A2, I'll get A1. So A1 times A3, well, that's A1 now. And then here I have A1, and then A2 times A3 is still A1, and A1 times A1 is A1. They're the same. And this would happen for any triple that you choose, for the kind of obvious reason that if you multiply anything together, you're just going to get A1. So like, it doesn't even matter like which three things you chose. I'm always happy to give more examples. I really appreciate the questions. They're what makes this really interesting. I mean, I think what I'm doing is interesting too, but the questions and that dialogue is definitely very fun. So this also, by the way, this is what's called a zero semigroup. This is okay. Maybe not the most exciting example, but it is a semigroup. It has an associative binary operation. So we can make lots of examples that aren't the nice sort of group examples where everything's a permutation, or all the rows and the columns are permutations. There are lots of examples like this. This is kind of the most extreme in the sense that like the product of any two things is just a single element, but there's a whole spectrum of different things in between that have different interesting structures. So that's nice. But whatever example we have, so now maybe I'll erase this just to maybe I'll just scroll down instead of erasing. I will just scroll down and I'll say, okay, so let's just assume we have some binary operation. Let's just ignore this up in the corner here because I'm at the end of this page. So we have some binary operation, and it satisfies this. Say it satisfies this associative property that if I do x and y first and then z, that's the same thing as if I do y and z, and then with x, like this. Okay. Well, I can actually make something from this which is sort of a more tangible thing in some sense, because this is kind of abstract. To say you have a set with some kind of multiplication or some kind of binary operation on it is kind of a little bit more abstract. So one thing that you can think about is, well, instead of just doing, like saying I can plug in A1 and I can plug in A2 and I'll get some result, whatever it is. Instead, what if we think about letting us plug in maybe fractional amounts of these things? So maybe I can plug in maybe I shouldn't go to fractional right away, but let's say I can have like 7 copies of A2. Let's say I can have 7 times A2. Now, that doesn't really mean anything per se at the beginning, but let's just assume that we can make sense of what 7 times A2 is. A2 is just some symbol, and let's say we can have 7 of those, whatever that means exactly. Well, one reasonable thing to say is that should be 7 times whatever f of A1, A2 is. So in other words, we can pull out constants. We can just declare that should be the case. And similarly, if I had 5 times A1, and then I wanted to combine that with A2 according to this rule F, we could also just say, the constants can come out of the first one too. And so I'll just declare that to work that way. Or if you don't like the F notation, what I'm saying is basically, if I do A1 times 7A2, that's 7 times A1, A2, and that if I do 5A1 times A2, then that's going to give me 5 times whatever I get when I do A1, A2. I can just declare that to be the case. And similarly, I can further extend this and say, if I wanted to do A1 plus A2, and then maybe I combine that with A2. Why not? I can say, well, that should really just be f of A1, A2, and then I add that to f of A2, A2. Or in other words, I'll just decide that this operation should like distribute over addition, basically. So like in other words, this is saying something along the lines of A1 plus A2 times A2 is just equal to A1 A2 plus A2 A2. Okay. So I can just declare that I want all of these things to be the case. Homogeneity. Well, yeah. I mean, this is this. I guess I don't know if I want to call this homogeneity actually. So like, yeah. I guess you could call this homogeneity. Yeah. Okay. I guess I'd say yeah. It's additive. Okay. Well, I know what I want to say now. I was being indecisive. So yeah. It is homogeneous in each coordinate. So in other words, maybe just for a little bit of an aside, let's see if I can get a new page here. If I have like some operation, maybe I'll call it G, just to make it something different. If the 5 comes out of the if the 5 just comes out, this is what's called homogeneous or homogeneous, depending on your inclination. This is like homogeneous of, sometimes it's called homogeneous like of degree 1. And then you can also have things that are homogeneous of higher degree, like if you can pull out, if the 5 comes out, but it comes out as like, it might come out as like a 5 cubed instead. That's possible. This would be like homogeneous of degree 3, and so on and so forth. So yeah, you can call this property homogeneity. And what I'm saying here is that like I'm making this homogeneous in each coordinate of like homogeneous of degree 1 in each coordinate. Yeah. So I guess part of the reason that I was initially hesitant is because there's another candidate for being homogeneous. Yeah. And this stuff actually this stuff about like degrees of homogeneity actually comes up when you're studying like there's like natural there's natural situations where this comes up. Maybe I'll just leave it at that for now. But like in studying linear algebra and differential equations, the degrees of homogeneity are a thing that you would naturally consider. But linear algebra is kind of about things that are homogeneous in each coordinate of degree 1. Okay, so now I'm going to make a little, and thanks again for the comment or the question or whatever. By the way, yeah, that was a good thing to bring up. So now there is a similar thing that I don't want, which is what is the thing that I don't want? I don't want that if you do like f of 2a, like say 2a1 and 2a2, I don't want that comes out as just a single 2. Like that's something that you might guess. The 2 should just like factor out and give us that. But I don't want this. I want each 2 to come out separately, so that if I were to do this, it should actually be a 4 here, not a 2, because I should have 2 times 2, not just a single 2. So it's homogeneous in each coordinate. But it's kind of a lot of words to say it's homogeneous in each coordinate. It kind of like distributes over addition, and I want that in the other coordinate too. And so let's see if I can get this to scroll down here. So what I'd like instead, or well, maybe not instead, but what I'd like to say is I want to, so what I really want to do is I want to make a bilinear operation from this function f that I have that just takes pairs of whatever these a things are to other a things. So something that does all the stuff that I just said is something which is called bilinear. That basically means that it's linear in each coordinate, or it's homogeneous and it's additive in each of the coordinates. It does the things that I said before. And so maybe I won't write it in full generality, but it means something like I want to extend this to an operation where I can do something like, if I do like 2a1 plus 3a2, and maybe over here I'll do like 6a1 plus a3, why not? This expands out as 4 terms, and you can think of it like you're doing 2a1 plus 3a2 times 6a1 plus a3, and then just distributing as you would usually. And that this function f is just telling you how you multiply the a1, a2, and a3 with each other. So, one way to write this would be to say it's, okay, you know what, maybe I'll ask for your input. Do people want me to keep writing the function f? Or, good evening to you in Brazil. I guess we're in the same time zone, I think. Right? No, not, well, I guess it depends on where in Brazil you are, but we're close at least. We're both in the Western Hemisphere here. I guess maybe the Eastern time zone is more where people live in Brazil. Not sure. But good evening. Let's see, I think I want your input at this point. Do people want me to keep writing the function f and thinking about it as something with slots? Or do you want me to write it as though it's a multiplication, and we know secretly in the background that this rule is telling us how we multiply the little a1, a2, a3, and so forth? Does anyone have a strong feeling about which one you like better? Okay, the multiplication seems more intuitive. Unless somebody else has a different opinion, we'll remember that if we actually need to figure out what a1 times a2 is, there's some rule that's chosen. I guess okay, now we have one of each. I think we might need a tiebreaker because the less secret one has a vote for it now. Is there anyone else who has a preference? Do you want to see it with the f and like it's a thing that's f with 2 things being plugged into it, or do you want to see it like it's multiplication? But secretly we know that when we want to write down something like a1, a2, that really just means f with a1 and a2 plugged into its slots that it has. The f helps me. Okay. All right. So I think that the f's have it. We will explicitly write the multiplication operation. Okay. Now I have a third thing that I can suggest to you, which I've realized. There's a third option. Instead of the choice just being between say a1 times a3 or f of a1, a3, there's also a third option, which is that I can use a multiplication symbol that's not a familiar multiplication symbol. For instance, maybe I could do like a little star each time instead of just doing putting them next to each other or doing the f. Does anyone like a little star better, or some other little thing? Is that a good compromise, or are we feeling ambiguous about that? So I can and I shouldn't just write a star itself. Sorry, I mean, instead of just putting a1 and a3 next to each other or writing the f, I'll do like a1 and then I'll do like star a3. Or I can choose another symbol. It just needs to be something I can reasonably write. Okay, we have one vote for the stars. I can also do an asterisk. I can do a triangle. My triangles might not be very pretty. I can do a little circle. Alright. Okay. So I think I think maybe this is too many options now. It seems like people were mostly fans of the less secret one, the less suppressed one. So maybe I'll go with the F. But then, if you're following along at home, you can always rewrite it as just the multiplication if you want to, or you can use something like a star, an asterisk, or something to remind you it's weird multiplication. But anyway, I think I'm going to go with just the function with the slot notation for now, since that seems to be the thing that people were most partial to. Okay, so but remember, I can always think of it like as just like a weird multiplication too. Because I mean, who wants to just do usual multiplication all the time? You know, like the the whole fun thing about algebra is getting into all the weird multiplications and making it making it really bizarre. All right. Well, anyway, that's always been what I found amusing. Okay, so since we're going with this, if I use all those rules I just said, it means, like, for instance, I'll do this addition first. So this is like f of 2a1, and then with the whole second thing, whatever the whole second thing was, plus f of 3a2, and then here we have 6a1 plus a3, and then I just kind of keep doing this. And so, for instance, I can pull out this 2 comes out, this 3 can come out, and then I can do the addition in the right hand component as well. So I can get 2 times f of a1, 6a1 plus f of a1, and then here's a3, and then all that stuff plus there's the 3 that came out, f of a2, and then 6a1 plus f of a2, a3. Okay, almost ran out of room. And then if you keep going like this and you use the rules, we'll see that, well, this 6 can come out, and I'll distribute the 2, and so I'll end up getting 12 f of a1, a1 plus 2 f of a1, a3 plus let's see, there's a 6 coming out here, so I'm going to get plus 18 copies of f of a2, a1 plus 3 copies of f of a2, a3. And so, assuming that I know what f is, and I know how to multiply the a1s and a2s and a3s together, then I can figure out what this expression is. And it's some linear combination, it's some, sum of these elements multiplied by, some counting numbers. And so, hey buddy, my dog wants to visit me. Let's see what's going on. I think he's curious about who I'm talking to. Let's see. Hey buddy. Who's a good boy? Oh, he's got his little ascot, or oh no, I guess it's not an ascot. It's like a what is this? A bandana. Your little bandana baby. Do you want to say hi to the people, Davi? You want to say hi to all the people? Okay, he seems uncertain. Okay, buddy. I'm gonna keep doing my stream. Okay. Who's a good boy? Oh. Okay. Alright. Yes, you're very cute. Okay. Alright. Who's a good boy? Yeah. Oh, he's got to shake it off. Alright. Oh, no, he's back. What's up, Davi? Do you want to just sit here while I do math? Is that cool, buddy? Yeah, you got it. Okay, I'm not really sure what he's doing now. So I'm just gonna head back over here. Do you want to sit here, bud? Do you want to just chill? Alright. I realized that this isn't entirely visible. Maybe if I scroll a little bit. There we go. So, well, that's nice. And so, oh yes, yeah, this is the dog tax. Oh, okay, bud. Alright. Who's a good boy? So a natural question you might have at this point is why? Why am I doing this? And so the thing is, although I kind of presented it to you, oh yeah, this is Dobby's stream, of course. We're all just living in it. So I presented this to you as just sort of this nonsense thing where I said I have an associative multiplication rule, and I'm going to somehow extend it to be linear in each coordinate. I'm going to make it this like additive, homogeneous thing in each coordinate, which basically makes it act somewhat like the usual multiplication of numbers. But what this means is that if we can do this with any coefficients, basically we have extended f to a what's called a real associative algebra multiplication. And basically, depending on your background, that might just be a lot of meaningless words. But the words basically mean that you can do pretty much exactly what I just did, where the coefficients can just be any real numbers. So that's basically if you want to know what a real associative algebra looks like, it basically is like what I just said. Define some multiplication on just some set, and then extend it in the way that I just did, and you'll have a real associative algebra. Now, there's a slight caveat that like not all of them are sort of perfect in the sense that the way that we set this up, A1 times A1 or A1 times A3, all of those products just give you another one of the A1, A2, A3. It gives you another one of those like basic elements. In general, real associative algebras don't have to have that, but still, this is a really good general picture for what those things look like. This is basically what real associative algebras look like. And so, well, okay, that's nice, but, I didn't invent real associative algebras. People have known about them for, quite a while. People have studied things somewhat at this level of generality since the 19th century, so that's not exactly new. But what is a bit more new is that I want to think about the real algebra version of the associative law. So remember, I said I wanted for this thing to have that if you did x and y together, and then you did that with z, you get the same thing as if you did y and z together and then did it with x in that order. And so, well, that was supposed to be a thing about the A1, A2, A3, and so forth. And so, like that's saying things to us like this. If I do A1 and A2 and then do it with A3, that's the same thing as if I, combine A2 and A3 first, and then combine them with, I wrote A3 when I meant A2, and then combine them with A1. And so, that's telling us about things like this. But what I'm kind of more interested in is thinking about what this looks like for the real algebra version of this. Sort of what the linear version of this looks like, where I'm allowed to do like, not just A1 or A2 or A3, but where I'm allowed to stick in here like something like 5 times A1 plus, 2/3 times A2 minus A3 or something like that. Like, where I can just stick in anything like that I want to. And so that's actually part of what I have typed up in my slides here, which I'm working on. So, I want to, let me see if I can go to something a little more detailed. Well, okay, maybe not everyone is quite thrilled at the summation notation, but maybe, okay, maybe I'll just walk through this. But I do have this part already in my slides. Yeah. So, yeah, so maybe I'll just explain what's on these couple slides, and then I'll move towards doing this calculation that I have started to do previously. All right, and again, if you have any questions, if you're just joining, don't forget that the conversation is an awesome part of doing this, and so even if your question is tangential or is some kind of digression, I'm more than happy to hear about what that is. It doesn't just have to be me lecturing at you. And it's also very helpful because I don't know what level everyone's at, and it's probably not reasonable for me to take a survey every time and find out who's had what class or whatever. So just ask me whatever comes to mind, and we'll see where it takes us. Yeah. So just don't be shy. This is what I'm here to do. It's not, it's a little bit like you've just happened upon me doing this research work, but you don't have to act like you're actually interrupting me. You're definitely welcome to ask whatever. But okay, so maybe I don't want to scroll down that far yet. So what do I mean? So I guess what do I mean in more generality by extending this? Well. So if we have the A1, A2, and A3, like I had said before for our example, I want to basically be able to extend this to something where I can say, choose just some numbers, like U1, maybe the 5 is my U, or well, I'll do it this way, you'll see, it'll be cool. So U1, A1, plus U2, A2, plus U3, A3. So in other words, just U1 is some number, like 5, U2 is some number like 2/3. U3 is some number it's -1 here. I just didn't put in the 1 because, it's -1. So, you can just have some expression like that, and we can combine it with another expression that's similar, like V1, A1, plus V2, A2, plus V3, A3. And basically all those rules that I described, if I'm going to write it out in more generality, it ends up saying that, well, okay, there's going to be 9 terms. I'm not going to actually do all the steps to expanding it out because it's going to take forever, but it comes out to be like this. Do U1 times V1, and then F of A1, A1, and then if I do U1, V2, and then I'll have F of A1, A2. It's just whatever subscripts are on these things is the subscripts that are on here. And so, if we use that summation notation, it ends up looking a lot more compact. But you can just basically keep doing this. Somewhere we'll get to have U3, U3 V1, and then F of A3. A3, A1, and so on and so forth. And finally, maybe the last one we'll have is U3, V3, F of A3, A3. But I'm not going to write out all the terms because there's 9 of them, and it's too many. I don't want to write it all out. But we can do that, and that's just like what the general bilinear multiplication looks like. You just choose whatever numbers you want for the U1, U2, U3, V1, V2, and V3, and you multiply it out, and you get that. So now when I say I want to understand what the multilinear version of this thing is, this associative rule that says we can sort of bracket the multiplication either way, I need to use this formula in order to do that, because I want to see what effect it has on all of those coefficients, like the 5 and the 2/3 and everything. And just as a reminder, just again, let me know if you have any questions, and we'll figure it out. Or I can do more concrete examples. Just want to, try to find some kind of balance, because if it's too concrete, then it might not be clear what the abstraction is that I'm looking at. But if it's, if it's too abstract, then we'll just get lost off in La La Land, and you'll just be watching me write symbols. So it's, somewhere in the middle would be good. But okay. So, you know what? I'm thinking maybe I should actually write down a specific concrete example of this, just to illustrate better what I'm talking about. I think this might be a little abstract, and people are just being shy. Of course, I can't say for sure. Maybe every single person here knows all about abstract algebra, and I'm just preaching to the choir. But I don't know. Okay. So let's see a slightly more concrete example. But I think I'm going to do one that only has A1 and A2 and not an A3 because that's just going to be easier. So let's choose a specific choice of what this function f is, and let's actually just make it so there's only A1 and A2. In other words, the set A is actually, I'm just going to do A1 and A2 just to make our lives a little bit simpler. And that means f is taking pairs of things from A, and it's giving us other things. So the multiplication table for f just looks like this. Now we have to choose an associative multiplication. So we can't just choose anything. Unfortunately, I can't just ask you to vote for like every single entry because we might get something that's not associative. But well, maybe I'll choose one that I know that's associative. That's maybe a bit more interesting than just some random choice. Let's say all these are A1 and this is A2. I'm allowed to do that. This is actually well, okay. This is associative anyway. A1's kind of acting like 0, you know? A1 times anything is itself. So any multiplication that includes A1 is just going to end up giving us A1 in the end. Like if I do A1, like A1, A2, there's an A1 in there somewhere, so I'm just going to get A1. Which means if you bracket it the other way, you're going to get the same thing. Oh. Well, anyway, you probably believe me. You probably believe me that this is also going to be like A1 times A1 times A2, because this is just A1. So it kind of acts like 0. And then the only other possibility to check to see if it's associative is if I do all A2s, because if there's at least one A1, it'll just absorb everything and become A1. And so if I do all the A2s, well, if it's all A2s, A2 and A2 gives me A2, A2 and A2 gives me A2, so it's just going to be all A2s no matter what. So this is definitely associative. So this is associative. Actually, it's kind of like A2 is kind of playing the role of the number 1, and A1 is playing the role of the number 0. But I'm just going to call them A1 and A2 just to be consistent with what I did before. Okay, so if I were to write out what the multiplication looked like for this one, well, I only have 2 of these things to choose from. So I have U1 A1, U2 A2, and then I could have a V1 A1 plus V2 A2. And if I expand this out, I'll get 4 terms because it's 2 and 2, and 2 times 2 is 4. So I'll get U1 V1 F of A1 A1, and then plus U1 V2 F of A1 A2, and then plus U2 V1 F of A2 A1, and then plus, I guess I ran out of room, U2 V2 F of A2 A2. And we're actually not done now because I can even express this more simply. I told you how to multiply all of the A1s and A2s and so forth together. So this, and this are all just going to be A1. So I get U1 V1 times A1 plus U1 V2 times A1 plus U2 V1 times A1, and then plus A2 and A2 gives me A2, so I get U2 V2 A2. And I can even make this look a little bit nicer if I want to by taking the A1 out of these, and so it says U1 V1 plus U1 V2 plus U2 V1, all of that stuff, which is just some number like 5 or a million or whatever, times A1 plus, and then U2 V2 times A2. So that's how you multiply 2 of those linear combinations. That would be the multiplication rule for this real associative algebra, and this would be two-dimensional real associative algebra because there are two things here. There's A1 and A2. So because there's two things in the original set A, that's why we have it's a two-dimensional algebra. Can we assume commutativity when it's a constant times A1? Yeah, that's a good question. So usually what's done is that we don't actually talk. We just don't talk about what it means to say like A1 times 6, for instance. We just don't talk about that, and we always just immediately bring the 6 over and just say, well, that's really just 6A1. So that's basically assuming commutativity. Yeah, so like that's, but it's just that we assume it so hard that we don't talk about that usually. We basically just always put the coefficients on the left-hand side. You can do something more complicated where you don't do that, but I'm not going to do that right now because that's a little bit outside of what I want to think about at the moment. But yeah, so we basically just assume that the coefficients always just go to the left-hand side. The actual numbers always just go to the left-hand side. It's already complicated enough. Why make it more complicated by changing that too? I'm not saying there's never a case where you want it, but this is already more than enough for us. So let's just stick to that. So let's not worry about that. The coefficients can always just come over. So this is some two-dimensional real algebra multiplication, and I can't really draw you a picture of the whole algebra itself because, it's a rule that takes pairs of things. Like basically, you have two different choices of a number, U1 and U2, and then V1 and V2, and then you get another pair of such numbers. So I can't really kind of draw you a picture of that because somehow that's really like taking a four-dimensional space to a two-dimensional space, and so I have a hard time drawing four-dimensional space very well on the screen here. I do have some techniques to visualize these things, but I think at the moment it's not. Maybe it's a little bit overkill. By these things, I just mean. Okay, well, I'm going to take actually, let me see what you want. What do people want? I can take an aside and tell you about ways to visualize high-dimensional space, or I can just continue doing the thing that I was working towards doing here. Does anyone have a preference? I mean, neither one's going to take the rest of all time, so we can see both things eventually. I'll just give it a minute. All right. So we're interested in seeing the visualization. That seems to be the vote. All right. So I will come back to this and how I can do how I can look at this example and try to figure out what the multilinear version of associativity is saying. That was the thing that I was originally trying to figure out all the way back here somewhere. Okay, well, we'll figure it out. Or here, I guess. I was saying I want to see what the multilinear version of associativity is. Yeah, so for this one I can actually think of them as 2D vectors. That's exactly correct. So for this one, I can think of each of the things that I'm multiplying as a vector, like in two-dimensional space. Or in other words, just a point in two-dimensional space. Like for instance, okay, maybe I'll do this first and then I'll do the more general visualization technique. If I want to think about what it looks like to do like f of like 2a1 plus 3a2, and then maybe a1 minus a2, why not? I can think of these as being points in 3D space, 2D space, 2, 3, and 1, minus 1. So I can actually think of this as being like, a point here, go over 2, and up 3, and this is probably not gonna be to scale. I can think of it like this point, or maybe an arrow pointing to this point, if that makes you feel better. But it's like this point right here. And similarly, I can think of this one as being like, go forward one, and then go down one. I can think of it as being like this point. Or again, if you prefer, I can think of it being like the arrow that points to this point. And when I multiply them according to this rule, well, if I use the formula that I had up here, this would be saying, let's see, I am going to have 2 times 1, and then plus 2 times minus 1, plus, let's see, U2 and V1, 3 times 1, times A1, and then plus, well, U2 is 3 and V2 is minus 1, so 3 and minus 1 and A2. So at the end of the day, this is going to be, 2 and minus 2, so 3A1, and then this will give us a minus 3A2. So that's what happens when you combine those. And that's like saying you get 3 minus 3. So it's like saying if you combine the 0.23 and the 0.1 minus 1, you get 3 and minus 3. And you can do the same thing for any other pair of points. It's just kind of hard to visualize the whole thing all at once because, if you choose any two of these, any point here and any point here, you'll get another point here. So it's like a way of, instead of multiplying numbers on the number line, it's a way of multiplying numbers on this number plane that's like a two-dimensional plane of, that you can think of the points like numbers. Similarly, by doing what I just described, we can make these real associative algebras of any dimension that we'd like. And so we can also make 3 or 4 or 20 million dimensional number systems that behave in some sense like the way that the usual multiplication of numbers works. So that's pretty nice. And that's in general what I was just describing, is how to kind of extend the arithmetic that you're familiar with to an arithmetic that lets you think of, instead of a number line of numbers, some higher dimensional space, like a 2D plane or a 3D space, or even like a 27 million dimensional space, whose points can be thought of as the generalized numbers, whatever exactly that means. And I mean, really, it just means basically what I just have here. You just write, some number on the number line, there's some real number times A1 plus some other number times A2, and maybe so on and so forth if there's an A3 and an A4 and so on. That's a good question. Is there a graphical interpretation of the operation F, like scaling or rotation, etc.? So in general, what I just described will always give you something which is the general procedure that I just described of starting with a semigroup with an associative multiplication on a finite set and then extending it to make it multilinear this way. It will always give you something which is multilinear. It'll always give you something which has coefficients that kind of look like polynomials like this in terms of the coefficients like u1, v1, u2, v2, and so on and so forth. So that actually will make this what's called a smooth function. And so it will vary nice, like the value of, the product according to F will vary nicely, like smoothly or continuously, like there's, maybe I'll leave out the exact technicality, but it will vary in a nice way with your choice of the points that you're plugging in. However, that nice way may not be as simple as just being like scaling or rotation, etc. I'm not sure if people want me to go this far off, or maybe I'll mention it later, since we'll probably have time, but I might want to say something else first. But there is a two-dimensional real algebra called real associative algebra called the complex numbers, where the complex numbers are things that look like a plus b times this I, which is an imaginary number. A and b can just be any real numbers. And so you can think about this imaginary number as being like a number that when you square it gives -1. In other words, this imaginary number I is kind of like the square root of -1. Maybe don't think about too hard about what having an imaginary number of apples would be, because you probably freak yourself out a little bit. But you can imagine that there's some kind of number like this. It's the imaginary number. And then you can do the same kind of multiplication. You say, if I want to do 2 plus 3 times the imaginary number, and then I want to multiply that by 6 minus, the imaginary number, I can just distribute it out, and I'll do the same kind of thing that I just did before, and say, I should get 2 times 6 plus 2 times, minus 1 times the imaginary number, and blah, 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 blah. Of course, an imaginary number of apples is just the number of apples that you have, or when you multiply, you multiply by itself, it gives you -1 apples. I mean, it's maybe a reasonable thought exercise. Like, if you think about it, it's not like it's something that's completely impossible to give a relatively everyday interpretation to, I guess, because if you have three apples, and I'm trying to think of an example that seems reasonable. Okay. All right. So I see there's another question, which is also a totally reasonable question. Maybe I'll say this silly thing about the square root of -1 first, and then I'll answer the question about why a plus b times the square root of 3 is still only real. So if I have 3 apples, and maybe I don't know, maybe I sell them for $2, $2 an apple, $2 per apple, then, that should give me $6. I guess I'm writing it on the right-hand side for whatever reason. So, on the other hand, if I owed you 3 apples, and they were, they were still $2 an apple, I'd owe you $6 worth of apples, and you could think about that as being the meaning of -$6. So that's probably fair, I guess. But if we want an imaginary number, well, I suppose then if we thought about it as being if I had, if I wanted to know how, okay, so I guess to get an imaginary number, I guess I would say something like, if, so I'll make a comment about the electricity thing as well. I'm trying to be silly at the moment, but I'll give I'll mention a more real thing in a second, a more real thing about imaginary numbers. So if I wanted to figure out something like how many, if I had the same, if I had maybe X apples, and each apple happened to be the same amount of dollars as apples that I had, how many apples would I have to have in order for me to, let me say it this way. If I owed someone apples, I had a certain number of apples, which could be negative. I could either have apples or I could owe someone apples, and each apple costs the same amount of dollars as the number of apples that I have for some, unfathomable reason, then I would need to have an imaginary number of apples, and they would have to cost an imaginary number of dollars in order for me to owe $1, because I guess I owed that many apples. I don't know. That's a little bit silly. Probably not the best way to think about imaginary numbers. But yeah, a slightly more realistic example was pointed out in the comments, and thank you for mentioning this. So using complex numbers or imaginary numbers, you can actually it's actually a natural thing to do in the context of electrical engineering. When you're trying to solve problems related to circuits, it turns out that complex numbers actually make things very nice. There are ways of not thinking about it using complex numbers, but the complex numbers really make a lot of the arithmetic come out quite well. And so there are a lot of reasons for this. I feel like it's a little too far afield, and this is maybe a little bit silly. Okay, it's not wrong exactly, but it's maybe a little bit preposterous. But yeah, so I guess that's all I have to say about that at the moment. But I do want to address the question about, well, what if instead of that imaginary number, what if we did like a plus b times the square root of 3? Like, what if I wanted to do stuff like 2 plus 3 times the square root of 3, and then like maybe I want to multiply that by like 6 minus the square root of 3. The question is, why is this still only real? If I did the square root of negative 1, then I would get these like imaginary numbers that couldn't be any real number on the real number line. But if I do this, then I still get real numbers. And the reason is basically that the square root of 3 is a real number. The square root of 3 is a number between, if you take 3 square root of 3 and you square it, you get 3. And so 3 is bigger than 1, right? If I did 1 and I squared it, I would get 1. And it's smaller than 4, and if I took 2 and I squared it, I would get 4. So the square root of 3 has got to be some kind of number between 1 and 2. So it's a real number. It's somewhere in the number line. It's somewhere between 1 and 2, and the square root of 3 is somewhere in here. Are you okay, buddy? Debbie, are you good? Oh, I think he just wanted to say hi. It's just some real number, and when you add real numbers and when you multiply real numbers, you just get other real numbers. So, no matter what you do with combining, square root of 3 with other real numbers, it's just still a real number. You can also just expand this out by doing the same thing I did before and say, it's 2 times 6 plus 2 times, negative 1 times the square root of 3 plus blah, blah, blah. And at the end of the day, you'll see that you just have a real number when you do all that. If you start off with a real number as your like extra coefficient, you'll just stay in the real numbers. I also saw that the duels that happened during the Renaissance in Italy were mentioned. Absolutely. Oh, good. Okay, great. Yes, I'm happy that this is helping for the first section of the first chapter of Axler to be understandable. I hope that it continues to be helpful. Yeah, you're already on your way. I mean, that's now you do have to make sure that you're young enough, though, is the thing, because you can't get the Fields Medal if you're too old. I think 40 is the cutoff. So if you want to get the Nobel Prize, the analog of the Nobel Prize for mathematics, you've got to do good work. Well, realistically, during your 30s. I think doing that work during your 20s is less common because it's too difficult, especially these days, to acquire enough experience to reasonably do that. I'm not saying it's impossible, and of course it's all very political and everything, but I think that generally speaking, people are closer to 40 when they get it, which is the cutoff. And of course, mathematicians realized early on that there did need to be an age cutoff, because otherwise it would turn into what a lot of political offices are, where you can't even hope to get into the position until you're 75 years old, and it would just be a real drag if every single generation was waiting for the next one to expire before you could have a chance of winning any of the prizes. It would just take forever, and people would get discouraged. But yeah, good luck, and make sure to thank me in your speech when you win the Fields Medal. Of course, I'll thank all of you if I win the Fields Medal too, but I don't think that's very I'm not going to say it's impossible, but I don't think it's very likely. My understanding is that it's quite fancy and political, and I don't think that, despite them branching out and finally giving one to a woman, I think that my personal attributes are not such that I would be likely to win that prize, regardless of anything that I did. Don't tell anyone I said that, though, because it's probably not really something that people, the Fields Medal people would approve of. Oh no, it's okay. Sorry, I'm saying inflammatory things now. Oh, good. Oh yes. Well, okay. So here's another aside. Well, as far as the proving pi is rational. So there's a joke about trisecting the angle and proving the pi is rational in the chat. And thank you for the mention in the footnotes, by the way. So it's true that you can't come up with a procedure using a compass and a straight edge for trisecting an angle. For taking some angle and then splitting it into three pieces that are the same size like this. But if you allow yourself to use an additional tool, and I actually don't know what the tool is off the top of my head, but if you allow yourself an additional tool that corresponds to some kind of algebraic operation that's not, that's actually not algebraic in the sense of the solution to this type of problem, if you allow yourself some sort of transcendental kind of machine, you can perform this. So even though it's not possible to, say, trisect this angle or square the circle, find a square with the same area as a given circle or vice versa, using compass and straight edge constructions like people did, for thousands of years. Even the ancient Greeks, like the Pythagoreans, they had machines that were somehow, they'd be composed of various, levers and things that would have some kind of writing implement on it, and they'd have some kind of, wheels that would spin it around and stuff, whatever. I don't really know what these look like. I'm just drawing some nonsense. But they had machines that could do a lot of these things, because it turns out if you allow yourself a couple of different kinds of motions that are not normally allowed by the compass and straight edge constructions of classical geometry, then you can do all this stuff. And people knew this, I think. They made these for this specific purpose. And so it actually, you can do these things if you're allowed some additional operation. And they did know this, and they actually made devices for doing it to see that you could do it. And they were just we don't know if you really need the machine or if it's just that we're not clever enough to figure out how to get away without using it. So I don't know. I thought that was kind of a neat aside, is that they actually were. They didn't always restrict themselves to the compass and the straight edge. They did use other stuff as well when it was too hard. They just never were able to figure out whether you really needed the compass and needed the additional tools to do the trisection of the angle or squaring the circle. As far as proving that pi is rational, of course you can always say pi is just pi over 1, but that doesn't make it rational. If you are able to prove that pi is rational, since it's definitely also irrational, you might have found an actual contradiction in math, in which case, as a professor of mine used to say, we would all be able to go home at that point, because the whole endeavor would probably be pretty lost if we were able to prove such a contradiction in mathematics. Our understanding of reality would similarly be in quite a bad state if that were to happen. So do let us know if you find such a thing. But yeah, the cheap thing of saying pi is pi over 1 isn't going to do it. Oh yeah, if you can prove a contradiction, then literally anything is true. So yeah, you would certainly get all the points back on your homework, because everything that's false is also true, and so forth, and so the entire thing would just be nonsense. And so you get all your points back. Everyone would actually have passed all their math tests, no matter what their answers were. I don't know if not giving an answer would count too. We'd have to think about that, but I think the world would be collapsing pretty bad at that point, so we probably wouldn't care. whether anyone passed their exam or not. But yeah. Oh yeah, and like so yeah, there's like this like Archimedean spiral that's probably not very accurate, but as yeah, was another good thing that was mentioned in the chat. There's mechanical ways of constructing curves that have these sort of irrational properties or transcendental properties that don't correspond to any of the classic like compass and straight edge things, and you're able to use them to do some of these things. I don't know a great amount of detail about this, but there's whole books on it if you really want to get into it, on either just like what you can do with a compass and straight edge, or what other tools can let you do, like if you can use like machines that can make such spirals and things in order to do other constructions that otherwise would be impossible. Yeah. So yeah, I mean, you can really get into it. Oh, by the way, I guess I should mention too, another motivation for studying algebra is there's an area of algebra called Galois theory, after Évariste Galois, who was a French mathematician in the 18th century. I think it was now I'm not remembering if it was 18th or 19th, but he actually laid a lot of the foundation for our understanding of these kinds of compass and straight edge constructions algebraically, and the techniques from that area are able to prove that, for instance, that you can't use the compass and straight edge to do things like this. Like you can't use them to like square the circle or trisect an angle or that type of thing. So they're actually it's actually kind of a very practical thing in that sense. Like you can use techniques from abstract algebra to prove that you can't do these things using a compass and straight edge. Thanks for checking. Yeah, so it was actually 19th century. It was later than I thought. But that makes sense because the 19th century was really when abstract algebra got started. So that was good. Thank you. Yeah, you can also see from Galois, according to what we have in the chat here, Galois lived from 1811 to 1832, and so he didn't live to be very old. Yeah, I see people already joking about the duel. So apparently he, when he was pretty young, 21 years old, I guess, he entered into a duel, like with pistols, because that's what they did back then, and he lost the duel and he died. And so he only lived to be 21, and despite that he did some really great math, which he sent off to older experts who were not in the business of getting into duels and being irresponsible young people, I guess. They were actually able to popularize his work, but yeah, he despite being good at math, he did not make the best life decisions and did not survive. I mean, maybe he would have said that it was worth it or something, but I would guess that he expected to win the duel and he did not, and so that was pretty bad. Oh my god. No, I don't know if I'm pro duels with pistols. I think that I would like to leave that in the 19th century. But okay, so that was quite a bit of a digression, but it was a good one. So maybe I will go back to sword duels. Oh, I see. Okay. Sword duels, I don't know. I mean, I guess you've got to be a lot more serious because it's a lot harder than using a pistol. But yeah, I don't know. I'm not much for violence myself. Okay, so maybe I'll go back to what I was doing here. And so the idea was that I wanted to understand what this associative law would mean for just some kind of well, if I were to take some binary operation that was associative, some semi-group operation, extend it to make a real algebra, and then look at what the associative law would be saying about it, that's what I wanted to do. And so I gave this example to give a clearer picture of what was going on here. And so now I'd like to actually rephrase this in a slightly different way. a different way that we can think about this is, if this was my original multiplication, say this is A1, this is A2, A1, A2, the example that we just looked at was where like A1 times anything was itself, and then A2 times A2 was A2. So one way that we can think of this is, like, if we think of it as actually being something that was extended to having these coefficients, we could think of this as telling us the fact that, for instance, I want that to be A2. We could think about this as telling us the fact that like A1 times A1 gives us 1 copy of A1 plus 0 copies of A2. And similarly, A1 times A2 gives us 1 copy of A1 plus 0 copies of A2. And then here, A2 times A1 is A1, so we get 1 copy of A1 plus 0 copies of A2. And finally here we get 0 copies of A1 and 1 copy of A2. So, well, I could write that way if I wanted to. And so then the idea is, well, that was for this specific example, but if I wanted to, I could just think in general, I have some multiplication on my set, say it's still the same set with 2 elements, just to make us, not have too many things going on at once. But I can think about that as really being a multiplication table where I have my A1, my A2, A1, A2, and what I'll say is I'll choose some coefficients, which I'm going to actually call F, and then like here maybe F111 times A1, and then plus F, maybe I'll make a little more room, and I'll explain in a second why I'm doing this and what F111 is. And here maybe F112 times A2, and then if I come over here, make enough room, similarly this would be F121 A1 plus F122 A2, and I'll fill out these other entries similarly. But you might now naturally wonder, what am I doing? What I'm doing is I'm saying each of these F sub a list of 3 numbers, these are just some constants, some numbers that I have. Like here, like F11 might be like 1. F112 might be like 0. F121 is like 1. So see, I'm just replacing each of those specific coefficients and just saying like, there's just going to be some number that is the coefficient. And I'm going to call that F111, 112, and so forth, because the idea is that like F121, for instance, this is the idea is like this would be like 1 if F of A1 A2 was equal to A1 1 1 or 1 2 1, and then it's going to be equal to 0 if F of A1 A2 is not equal to A1. So it's going to say either yes, it is equal to A1, or no, it's not equal to A1. And that's like exactly what we're seeing up here. But then once I do that, I can say, but then maybe I could think of it that way, like if I started with an actual operation, but I could also just imagine I could choose some numbers here. Maybe they're not even zeros or ones. Maybe they're 5 or -2 or 16 or whatever. And I would still actually possibly be able to have an associative algebra operation. But my question is, what numbers do I have to put in here to get an associative operation? Like for instance, we knew that the reason that we knew that these numbers worked 1 0 1 0 1 0 0 1 was because this was an associative operation over here. Oop. Oh, I just went back a page. No, I went back to the beginning. I've never used the pages here like this. Oh, that's nice. Okay, well let me find where I was before. Let's see if I can find where I was before. Okay, good. So the reason that we knew that this choice worked was because this was a semigroup. This was already an associative, an associative thing. Oh, huh. I was trying to do the undo, but I feel like it's just taking me back and forward on the pages now. Alright, well, whatever. Let's see. Can I undo this? This looks like this is undo. Okay. I don't know what was going on with that, but that's fine. So, oh yeah, thanks for the comment about making the notebooks change and change the paper to be lined if I want. I actually don't want that. I saw that that was the default, and it stressed me out a little bit because when I was like a little kid, I did use lined paper, but now I've been just writing on just whiteboards and blackboards for so long with no lines that it like stresses me out. I need to just be free and be able to write all over the place with the size of my text changing radically all over the place. The lines are just too much for me. Yeah. So the question, so we're now getting closer to what the actual question is. The question is, which coefficients do I choose? What do I choose for these numbers? F111, 112, 121, 122, blah, blah, blah. Which ones of these do I choose so that I actually get an associative real algebra? How do I make the associative law happen? These choices we knew worked just because we knew the original multiplication was associative. But for these ones, so like this one, for instance, would be like F1 or F211 A1, F212 A2, and then I'll just finish out the rest of it, I guess. 221 A1 plus F222 A2. So the question is like, what choices of these F, I, J, K, whatever they are, what choices will give us an associative operation? It's a reasonable question. Some of them will give us associative operations. We've seen an example, but some of them won't. They'll give us a multiplication that doesn't satisfy the rule about saying that x times y times z has to be the same thing as x times y times z. So that's possible. We might make some choice of these coefficients, these F111 and so forth, that just make this doesn't always happen. Sometimes it'll fail. And so it turns out that we can actually write down an equation that exactly expresses when our choice of the Fijk, when those choices will give us an associative operation. So in other words, the basic question is which list of these things, maybe F111, F112, blah blah blah, and so forth, all of those, all the way up to F222, which things like that give us associative operations. Okay, so I claim, I haven't actually done this for you yet, but I claim that I can write down a single equation that will actually express when that occurs, and that's the thing that I'm working towards doing. But maybe before actually trying to find what that equation looks like, I would like to point something out to you, which I think is amusing. Are there any questions about this, though? I feel like I should check in every once in a while and see how we're doing. Oh, and for the first time ever on this stream, I think I'm going to drink some water. So I went the whole 3 hours last week without drinking any water, but this time I'm actually going to drink water. And be prepared, because my water bottle does scream sometimes. It goes like, tss, like, I don't know, it's crazy. We're going to see. Yeah, it did it a little bit. I've been asked before if it's like a machine or if it's something helping me drink. No, it just screams. There's not really any deeper explanation than that. My water bottle just screams at me when I drink out of it. But okay, so yeah, just let me know in the comments if you have any other questions or comments or anything. But this is the question. This is the question I'm trying to describe right now. Oh yeah, water bottles frequently scream, apparently. I guess I'm not alone in this. Oh yeah, okay, so thank you for the question, comment, yeah, about like you don't disagree with anything I've said, but it still seems like maybe not quite as motivated. Like the question about what does this mean to me is a great question, and really because in order to understand why I'm trying to do this, you want to understand what it means. It's not enough to just follow it technically. You also should follow the intuition, which is probably part of why it's really hard to teach machines to actually generate new mathematics because they, they do not possess that kind of intuition or intuitive understanding or drive to do something, and so because of that, they can be helpful, but they require a great deal of babysitting because they're not motivated on their own like we are. Maybe I won't go on too long about that, but yeah, this is really what sets us apart, is our ability to have an intuitive understanding of what we're trying to do and be driven and motivated by that. Okay. Well, so I mean, I guess whether you're following technically has a spectrum of possible values, if, I mean, you don't want to overestimate yourself. Maybe I'll say something else a little philosophical. You don't want to overestimate yourself and just assume that you do understand everything perfectly clearly. If you can actually do or reproduce the calculations, the explanations, that's good, especially if you understand what you're saying when you reproduce them. But, you don't want to be overconfident and miss things because you're being too confident and you're not really making sure that you understand. But you also don't want to be too sort of too timid or too doubting yourself too much, or else you'll get stuck and you won't be able to go. So what I tell my students sometimes, and I didn't come up with this, so don't give me credit for it, but mathematics is actually like fighting a battle. You don't just proceed in this orderly fashion from one thing to the next. You might make an advance and take some territory only to get pushed back and you realize you don't really understand like you thought you did. But then you make another ingress into the territory you're trying to take over, and over time, if you persist, you can actually make legitimate progress. Okay. I said I wasn't pro-violence, I guess, and now we're yeah. So like a duel, even. Yeah, I suppose it is like a duel. All right. Well, still, I'm only in favor of this metaphorical violence. I will not be dueling anyone, whether it's with swords or otherwise. Okay. So, all right. So the question is, what does this mean? Well, right. Yeah. You just got to keep at it, really, and you'll make it. It doesn't matter how many times you've been defeated before. It's mathematics. You can always get back up and try it again. It's really quite a pure art form, if you think of it as a form of art, because you don't really even need the pen and the paper. It just helps you to keep track of what you're thinking. You only need a mind, and despite what some people say, I truly believe that anyone can do mathematics if they're so inclined. If you just, I'm not saying it's not harder for some people than others, perhaps, if you have different, like some kind of learning disability or something, but I do believe it's possible for everyone if it's something that they really desire and they have the time and support to pursue it. Okay. So let me before we all forget what I was just talking about, and I just keep saying these philosophical things. So the question is, which of these lists of coefficients give us an associative operation? So why do I care about that, or what's the intuition behind that? It's that consider. I guess I should put an N in there. Consider the set of all these F. Here, I'll actually write it out just for more emphasis. Actually, the set of all things that look like F111 F112, F121, 122, just all of those coefficients. There's 8 of them in this case. 211, 212, 221, 222, such that here maybe I'll call this F tilde just for fun. I'll give it a little hat. I'll say consider all the set of all of those choices of coefficients with the property that I accidentally moved my page. With the property that such that the maybe I'll just say the resulting real algebra is associative. Okay, so we can consider the list, all of the lists of such coefficients. Oh, and by the way, these are called structure constants. So each list of such numbers, if I could spell constants correctly, that would be good. These are the lists of all the numbers that would give us an associative multiplication on, like, in this case it would be like on the two-dimensional plane, basically. Like each of our things that we're plugging in is like a point in the 2D plane, like we saw before. So we can consider the set of all such lists, and I'm going to just say real numbers. I was just giving integer examples because I wanted to just keep it simple at first, but I do want to allow these to be any real numbers, actually. I'm just going to let them be any real numbers. And so the intuition for why I'm considering this is the following. If I think about this list of 8 coefficients, I can think of this as a point in the space R8. This is 8-dimensional space. Just like R2 is 2-dimensional space, or R3 is 3-dimensional space, 8-dimensional space is nothing but lists of 8 numbers, 8 real numbers. It's the usual space that we think of. So each point that corresponds to an associative real algebra, that is the structure constants for an associative real algebra, that's a point in 8-dimensional space. That means this set of all points that correspond to these that correspond to these real algebras that are associative form an actual object. So the things that you're multiplying in the real algebras are points in 2D space, like we saw back here, somewhere, if I can find it. Oh, did I go too far? Where's my... Yeah. So like we saw here, the multiplication for a single real associative algebra would be like something that took a point from 2D space, another point from 2D space, and you combine them and you get a new point from 2D space, like we saw in our example. But if you think about the structure constants themselves, they form each list of structure constants, each tuple of these constants, is a point in 8-dimensional space. In other words, you can think of, the algebra is basically given just by choosing these numbers, and then the multiplication is determined by that, right? Once you know those coefficients, you know the whole multiplication. So each of those lists, like for instance, this one that we did the example of before, it'd be the list that goes, 1, 0, 1, 0, 1, 0, 0, 1. That's a point in 8-dimensional space, and that point we can think of as being the real algebra that is given by this multiplication. The use of the word structure here, I actually don't know where this use of the word structure originally came from. It's just that these coefficients, such as these, are called structure constants sometimes. But it doesn't necessarily have a technical relationship with any other mathematical definition of the word structure that you may have heard. It's just structure kind of is a word that's similar to like normal or regular or algebra. that is used in like 80 different ways in math that don't necessarily have any kind of technical relationship with each other. There are so many things that are called algebras that have nothing to do with each other specifically, except that they're all generally related to multiplying things together somehow. And so you can really go, you can really get into like, oh, well, that kind of algebra really is an algebra in the other sense because blah, blah, blah. But yeah, this is actually another reason why teaching machines to do math like we do math is hard, because we actually don't give unique names to everything. We tend to reuse the same words over and over again. Kind of like how there really are many different types of vehicle that we all might loosely refer to as a car, and we all kind of know what a car is in the context of when there's a car around and we're talking about one, but car by itself is not really very specific if you think about it, and we have similar things in math, you know. There's actually quite a broad spectrum of things that any particular word can mean, especially the common ones. Yeah, I'm happy to answer questions about the paper I linked to. This is connected to that, by the way, but the use of the word structure in that paper is kind of, it's a coincidence that these are also called, it's kind of a coincidence that these are also called structure constants. Maybe I'll just say kind of and leave it at that. Yeah, I apologize for this. I'm not really responsible for it. I just work here. But this is the nature of things. It's like how the word I've actually used, even in this live stream that I'm doing, I've used the word algebra in multiple different ways and not made a big deal about the fact that they have different technical meanings. Oh, good. Yes, please do change it when you get the Fields Medal. I will warn anyone, and on a serious note, I will warn anyone who thinks that, well, why don't we just sit down now and use the internet to like come up with consistent names for all the things and make sure that there's no conflict between all the different names and everything. Doing that is like, if you were to say, well, you know, there's certain words in English that have multiple meanings. Like the word run actually can have a lot of different meanings, right? There's a difference between going for a run for, you know, some kind of like, you know, you're running for like an elected position. You can run a computer program. You can have a run in your stockings. Like all of these things are called run. Well, why don't we just make up a different word for all of these different things, and we'll just decide on that, and then it'll be fine. What happens in reality is that language is... okay, I actually don't know that XKCD. Would you mind linking it? Apparently this is XKCD 920. Oh, no, I do know it. I don't have to see it in order to know it. It's standards. Why don't we take... It's got to be the standards one, right? Why don't we take all the competing standards and we'll just make one new standard that... Okay, good. So yeah, XKCD 927. I'll link it in the YouTube video when I post this on YouTube. Yeah, we'll just make a new standard that deals with the conflicts with all the other standards, and then it'll be fine. It'll just be, you know, there'll be no problem at all. But of course, we've just added another standard. So there's all kinds of like, you know, I mean, it's similar. It's similar to trying to regulate a spoken language, and it's not even like it's French or something where like there's a small enough group of people and people kind of agree that okay, there's like an institute that decides if something's a word or something. Like math is a lot bigger and a lot less organized than French, I think. In some sense, you know, like there's people who do math in all different languages, and if you listen to people who speak multiple languages talking math to each other, it will kind of oscillate between words that are English words or words that were originally French or Latin or even Arabic or, you know, what have you. You know, it'll be like math terminology, so maybe some English, maybe some French, some Russian, and like, you know, unless everyone speaks the same like language fluently, like maybe English, and also uses all the terminology from that language, it usually just turns into like a real mishmash of different things. Because like some people might speak Russian fluently, but they only know math and English, And so when they have to talk math to somebody else, even if they're speaking Russian most of the time, the English math words will come out. But of course, the English math words are really French or Latin or whatever. And so it's just, yeah, it's basically an impossible thing to regulate or organize in that sense. So yeah, unfortunately, it's pretty hopeless to control the words that people use. There's also a lot of competition for cool words like structure or algebra or whatever cool word you come up with for a math concept. So it also is kind of like naming babies. Like you can't tell people your cool baby name because they'll steal it, right? You have to make sure that you have something that's about to come out that you're ready to name, so that you can try to secure that word, because there's a lot of competition for the good words. And like, I just sit there like going through the thesaurus sometimes saying, okay, I'm going to try to make that a math word, I'm going to try to make that a math word. Like, it's, and you can see a lot of them are used up. Like, a lot of the cool ones already got used up. And you can always go to other languages other than say English or Latin or whatever, but it's always a balance, because you want to appeal to words that people understand too. So if you get too niche or too archaic, then they're not going to recognize how cool your word is necessarily. Anyway, I have fun naming concepts. I think it's cool, but okay, that's probably more than enough about language, I guess. Yeah, so there's these structure constants, and you can think of them as points in 8-dimensional space. But that means each real associative algebra is like a point in 8-dimensional space. In other words, there is some kind of shape, I don't know what it looks like, maybe, I don't know. It's some crazy, high-dimensional thing, who knows, something we don't, maybe we don't know what it looks like very good, some shape in 8-dimensional space, in R8, whose points are all the real associative algebras. In other words, okay, and I guess I should say algebras of dimension 2. Everything I just said was for the ones of dimension 2. The ones that the things you multiply are like points in 2D space. So, I mean, that this picture is probably not anything like what it really looks like, but I don't really have a good picture to show you what it really looks like. It's a shape that exists in 8-dimensional space. Oh yeah, I always put these on YouTube. Yeah, that's a good question, and yes, I always put these on YouTube. I'm recording, unless something catastrophic has occurred. Yep, it looks like I'm still recording, and I should have a nice big 6 gigabyte video to post on YouTube after this. So yeah, you can check it out, and within reason, if I can remember things that were posted, like the XKCD, I'll try to find. I will post those in the description of the video as well, so that you can go to the things that were linked in the talk. You don't have to, or in the live stream or whatever this is. It's not meant to just be me lecturing you. Oh yeah, sure, of course. Yeah. Thanks for watching. But yeah, so yeah, and just of course continue to ask if you have any other questions or make any other comments or anything. I do hope that YouTube won't. I don't know where the line is. We've talked about duels and stuff in this video, so I'm not sure how YouTube or Twitch will feel about that. I mean, Twitch has got to have like people doing like shooter video games and stuff, so I think that they probably can't be too draconian about it. But I do know that on some platforms like TikTok, people aren't allowed to say certain words. Like if I was on TikTok, I think I couldn't talk about. I think I couldn't talk about things like there's something. Don't ask me to actually define it, but there's something called a killing form in mathematics. I think probably that would be forbidden. For instance, I would have to say an unaliving form or something, even though killing is the name of a person, and not it's not referring to something violent. But anyway, I don't think the same kind of censorship is present here. But yeah, there's some shape in R8 whose points are all the real associative algebras, and so of dimension 2. And so the reason why I think that this is cool, to get back to the question of like what is this for, the idea is then the following. I can actually write down an equation for what the points are the solutions to some algebraic equation that I can write down. And so if I could understand this shape, or if I could understand the equation that defines this shape, I would be able to understand, in some technical sense, all of the real associative algebras of dimension 2. And there's a similar shape for dimension 3 and 4 and so forth, but just like how the one for dimension 2 is a bunch of points in 8-dimensional space, the one for dimension 3 would be a bunch of points in 27-dimensional space, and it gets big very fast. But yeah, so the idea is if I could understand that shape, or the equations that define that shape, then I would basically be able to understand all of those algebras at once. Like, understanding that shape is the same thing as understanding all of those algebras. And so that's the idea then. If I can somehow understand that shape, then I can understand all of these algebras simultaneously. And the hope is that even if I want to just understand finite algebras, like just the multiplication that we started with back here, the hope is that by sort of viewing this multiplication table as being a point in 8-dimensional space, in other words, a list of numbers like that which also is binary, which is sort of, nice in the sense that it's also like naturally pretty computery, if you prefer to think of it that way. If I could understand this object, I would be able to understand all of those things. Like, somehow deeply understanding this object is the same as understanding all of those things. In particular, you can start getting into things like, well, if there's this, this shape that somehow is the shape of, here, I'll just draw it as a blob now. If there's some shape, maybe it has some holes, I don't know. Maybe it has some spiky parts, I don't know. It doesn't have to be like a nice smooth thing like I was talking about before. Maybe it's got some angry spiky parts on it. If I have two different points, maybe this is some multiplication I call f, this is some I call g. They might be able to be deformed into each other by taking this like path where f, if you think about moving along this path, you're getting algebras that are like little tweaks from the one you started with until you get to the other one. And I can ask things like, which real associative algebras can be deformed into each other? Those would be basically asking which of these things can be deformed into each other is like the same thing as asking what are the path components of this space. And so it's possible, at least, that by understanding this shape, we would be able to answer questions about the algebraic structures as well. Or understanding the symmetries of this shape would somehow help us understand the symmetries of the structures. So that's kind of the big picture goal. So maybe at this point, are there any questions or comments about that kind of big picture thing, or just anything else at all in the entire world? This picture is definitely not accurate. How do we know? Do we know how many contiguous components are in this 8-dimensional shape? Well, okay, maybe I'll say first of all, the shape itself. Okay, so I guess I want to just maybe make a comment about the dimensionality of it first. So just like how there's a distinction between like, oh, okay, that's meant to be a donut. So if we have something like the donut or the like 2-dimensional sphere, like these live in R3. Like, they're 3-dimensional in that sense. Longer. These things are two-dimensional surfaces in the sense that if you look up close, like we talked about in last week's live stream, actually, if you look up close, each little piece of this thing, like if I were to just take a little segment of this out, it just kind of looks like a little piece of 2D space. it looks like, you know, it looks like two-dimensional space close up. And so actually, I will address the question about how many connected components there are, but maybe an even more basic question is what is the actual like the actual dimension of this thing, like topologically, because we know that the shape lives inside of 8-dimensional space, but for all we know, yeah, it could be a 7-dimensional surface, or it could even be lower dimensional. Of course, you know, you're perfectly welcome to think of like you can have like curves inside of 3-dimensional space. It's totally possible to have some kind of curve here. Maybe I'll even have it cross over itself just to show, you know, maybe it's in 3D. You could have some kind of like knotted thing like this that's like a thing in you know, in 3-dimensional space. Like, why not? But this looks like, you know, this looks like 1-dimensional space close up. So you can have things that look like you know, or just the real line. So you can have things that look like lower dimensional objects in higher dimensional space. So without saying any more right now, all we know is that this looks, you know, this is something living in 8-dimensional space, but it's probably lower dimensional. Like, it could be a 7-dimensional surface, or it could even only actually be 4 or 5-dimensional. So we don't, you know, at the outset we don't necessarily know what the dimension is. And as an extra twist on this, we actually don't know that it has to be a surface at all. Like, it doesn't have to be something that's like a nice smooth manifold like I talked about in my live stream last week. It turns out that it is something called an algebraic variety or an algebraic set. But algebraic sets don't have to look like this. These things kind of are smooth looking things. Algebraic sets can look like things where you might have like a circle, but maybe there's also like a line, like a curved like parabola touching it. And so if you look close up, most of the points look like line segments close up. But if you look around this area where they're touching, this piece kind of looks like an X. It doesn't really look like the real number line. And so this isn't a manifold, but rather something else. These algebraic sets actually can be more complicated, unfortunately, than just being manifolds. And so when we ask about the dimension, then we also have the possibility that there are pieces that have different dimensions to them. Like, there might be pieces that look like 1D like this, and there might be some isolated points that are 0-dimensional, or in the higher dimensional case, like in 8 dimensions, there's even more possibilities. It might have a big chunk that's 6-dimensional, and then another chunk that's 4-dimensional, and we just have to live with that. These things are, in addition to being algebraic sets, they're also what are called pseudo-manifolds, and so there is a way in which they're similar to manifolds. And that's also related to the paper I was talking about last week. So it's gonna all come together eventually, but it's gonna take a hot minute, but it will come together eventually. So there are many considerations for what the dimension of this is, and I don't know the answer to most of them, even for this specific small case. What I did do in my PhD thesis, the part of which is also what the paper is that I linked in the pinned comment on this live stream. So what happened, I guess maybe just to summarize or to discuss where I'm going, is that I found equations that would define these algebraic sets. Like, I found like the equations that the points on these things had to satisfy. And I didn't just do this for associative real algebras. I did this for any kind of algebraic property that you could define, basically, in terms of equations. Not just associativity, but like commutativity, or even some really strange algebraic property. In other words, like, if you said to me, oh, you know, I'd like to really understand I'd like to really understand operations like that take 6 things and give you back a single thing, and I want them to have the property that if I do f of x, y, z, u, v, w, I always get the same thing as if I did like f of x, y, z, u, v, f of like x, 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 w. Just any random thing like this that you can come up with and say, I want something that does that. And I want to do the real version of that. I want to do the multilinear version of that. I can say, okay, I can write down conditions that would have to be satisfied by the structure constants for such a thing, and I can actually write down a formula for what the points are in some high-dimensional space that correspond to such operations. I can do that, and it's basically the same way that I would do it for associativity. I can do it for any such property that you would like, even for operations that take more than 2 inputs, even for like a multiplication that somehow takes 6 things together all at once. But despite being able to write down these equations, and I understand that like the space of points that satisfy these conditions is it's this object that if I understood it, I could understand the algebras. The problem is that I can't understand that object very easily. Even in the relatively simple cases of like doing like associativity, like what I did before, this shape remains pretty mysterious. Oh, by the way, I should also say that this shape is sometimes called the moduli space. People have thought about this specific one before. I think the general description is not something I've really seen, like for the generalization that I was just discussing, but people have described this explicitly for, at least for the associative real algebras. This is the moduli space of 2-dimensional real associative algebras. And you can have a similar moduli space for any dimension. For 3-dimensional real associative algebras, 4-dimensional, whatever. So the thing is, even though I know a formula for what these structure constants have to satisfy in order to be a point on this moduli space, I don't really know how to use many things that already exist in order to understand things like what are the connected components of this shape, to get back to that question. It's not immediately obvious how to go from one to the other. So maybe now is when I'll mention algebraic geometry. Do we have any algebraic geometry people in here? I know that some people had been doing some algebra, so I don't know if anyone's been curious about algebraic geometry. Well, when I came across this, I was curious. I was curious about whether algebraic geometry could help me. So algebraic geometry says something like, well, if I wanted to understand the solutions to some equation, like x squared plus y squared equals 1, well, we know in this instance that it gives us a circle of radius 1. But what we can do is instead we can think about this algebraically by saying, well, what if I were to think about, for instance, thinking about this what's called this polynomial ring, where I basically identify x squared plus y squared with 1. In other words, I'm gonna quotient out, or kill off if you prefer the violent terminology, x squared plus y squared, say minus 1. I want to make that 0. In other words, basically, I'm allowed to do arithmetic with polynomial expressions like this, and that involve x and y. Maybe I'll do this like, say, y. This is y squared minus xy. But if I ever get an x squared plus y squared, like I add these together and I say, xy and minus xy cancel, I get x squared plus y squared. Well, I know that x squared plus y squared is supposed to be 1, so that's actually the number 1 in this quotient ring, it's called. And so, or coordinate ring specifically in the algebraic geometry sense. And so I thought, okay, this is what algebraic geometry is all about. And if you've seen, there's lots of, it's something that I think is, maybe people find very interesting, because of how abstract it's supposed to be. And, Alexander Grothendieck was very famous, and he built houses that people live in, metaphorically, I mean, even that paper that I linked that's related to things I'm talking about was from the Bourbaki group that, he was in, and, a lot of them did algebraic geometry, and it was very, it was very famous, it was very fancy. So when I was early on in grad school, I thought, okay, then I'll learn algebraic geometry. And so I started reading about these things, and what I discovered is that, you kind of need to be able to understand the structure of this coordinate ring algebraically in order to understand the shape, like this, we already understand the circle for other reasons, but you have some kind of equation like this. If you can understand this coordinate ring as an algebraic structure, then you can understand the original shape. The problem is that the equation that I want to use, or the equations that I want to use, are extremely complicated compared to this. And so when I went to try to understand the coordinate ring, what I said was, oh no, I need to understand something algebraically about these equations and how they factor or something like that, like how these terms factor or something like that, and I can't understand that at all. And so it was just too complicated. I mean, think about something like this, x squared plus y squared, maybe there's some other terms like plus 6xy or whatever, but instead of just 2 variables, you have 8 variables, which are these variables, f111, 112, 121, blah, 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 and you have some complicated equation that involves all of those things, or some complicated formula that involves all those things, and I need to make the coordinate ring with that. And the problem became that if I could understand the structure of that ring, then I would be able to understand my shape and use algebraic geometry to understand my shape. The problem is that I can't, at least, I haven't tried to learn or do algebraic geometry for the specific purpose or for any purpose since I was early on in grad school. But the problem seemed to be that I needed to understand those equations in order to understand the shape, but I can't understand those equations. And so I was in this catch-22 where it's like I'm trying to understand the points that satisfy these equations, but I can't understand the coordinate ring any better. And so I think this is kind of a typical way that you can get stuck mathematically, is that you want to understand something and you think that you can use a tool for it, like algebraic geometry. But it seems like in order to use that tool, you would need to already understand the thing that you're trying to use to understand it. And so then you just go, oh, I don't think this is working. Now, it's possible, since I didn't already know algebraic geometry when I first tried this, it's possible that there is a more clever or advanced way to use it to understand these things, which I never realized. However, I do have some reasons for thinking that it's not that easy, and by that easy I mean it's not like if at least this is my impression still, if I just gave this general thing to someone who does algebraic geometry, they would not just say, oh yes, I can obviously describe to you things like what are the connected components, what's the dimension of the thing. I don't think that they would say that. And the reason is that, there are a couple reasons. So one reason is that people have studied this exact shape before, and I've tried to find, I've looked off and on for literature related to this. In the noughties, in 2006 or something, I'm not sure exactly, I don't remember off the top of my head, but sometime in that vicinity, some people finally did actually figure out what the open components of this shape were, this specific one, the moduli space of two-dimensional real associative algebra is. Those people, and maybe I'll post a link to this paper in the video description as well. Oh yeah, yeah, that's a good comment. It would be neat for me to actually talk to another mathematician and try to learn stuff from each other. Yeah, it would make the difficulty higher because I mean, we could choose something that I have like a more basic knowledge of, like algebraic geometry. But the issue would kind of be that because I have so much more experience with related things, my progress in it would be extremely rapid compared to someone who was like just starting grad school, or like was otherwise earlier on in their mathematical career. So it would make it more intense as well. Watching a fully, sort of a more fully developed mathematician learn a topic is not going to be the kindest introduction to the topic, because that's the whole thing, is basically practicing, not just developing new stuff, but you also, practice consuming stuff that other people have done very quickly, and so the progress would be pretty intense. I mean, it would be basic at least for a little bit, but it probably wouldn't stay that way, because then I would start saying things like, oh, I see, so that's really just this other technical thing that I've seen, but maybe you haven't. And then they would say, yes, it is. And I go, okay, great, I understand this completely now. Or at least more completely. So yeah, it's kind of a double-edged sword there. It would make it could make it pretty interesting, but it also could make it quite intense. But yeah, so people did eventually figure this out, in the sense that they figured out what the open components looked like only in the two-dimensional case specifically, and that was just a whole paper. And unfortunately, as you can see, I'll post the link in the description, since I don't know if I'm gonna instantaneously be able to find it if I look it up right now. But what you'll see is that they needed some very special properties of specifically the two-dimensional real associative algebras. Okay, good question. What do I mean by open components? I mean that like in like the one-dimensional example. If this goes on forever, like this parabola thing, this might be like a component, like an open component of this thing, or maybe I guess, okay, that's maybe kind of degenerate, but just basically a component that inside of the shape is an open set topologically. I believe that's the exact thing that they found. So like so maybe the question is, like, as opposed to what would be a non-example? So like it might, I believe it's been a minute, but I believe that they just found these sort of big chunks like this. But it's possible that there are other points, like conceivably there might be other points that are just like some individual point or something, or some piece that's not that's not like some nice shape like this, and they didn't find all of those necessarily. I think they just found like these big chunks. So that's a little bit vague. I wouldn't take my word on it 100%, but I believe that's what they described finding, is all of the nice pieces that were like open sets inside of the moduli space, like topologically. Yeah, sorry, I don't have a much more specific description than that, but it's possible that what I just said was technically correct. But yeah, I'll post a link to the paper, and so you can see. But and thanks again for the questions. I'm always happy to try to answer, even if I'm not 100% sure. But I'll also tell you that, so that you have some kind of metric for how strongly to believe in something I'm telling you. And I'll try not to doubt myself either when I do definitely know something. Oh, what's up, buddy? Do you want to come say hi? I think my dog is getting reckless. Or not reckless, restless. Hey, Dobby. Who's a good baby? Who's a good buddy? He just wants pets. So here's the thing, though. This paper was cool. However, what they did only worked in 2 dimensions, because what they did was like, basically they said something like, there's only really 2 types of real associative multiplication that you can come up with fundamentally somehow. And they showed, in 2-dimensional space, only for these 2-dimensional ones. And so they showed that every other operation that could be obtained by deforming, one, like a typical operation, I guess I'll say, you could always kind of break things into being made of one part that was one type of multiplication and one part that was another. And so I'm going to leave that as pretty vague, but basically they noticed that there were these two special types, and basically every other associative real algebra was made by combining them somehow, like combining their multiplication rules somehow. And so they really didn't understand the shape by understanding the equations I was talking about. They understood the shape by understanding the algebras themselves. And from my perspective, that's kind of cheating, because my goal is to use the knowledge of that shape and the equation that defines it to understand the algebras. Their thing only worked because they were able to understand the algebras directly in that specific case, two-dimensional real associative algebras. But that doesn't generalize. So this is a common thing that happens in math, where like you can do something in some small specific case, and in this small specific case is in 8-dimensional space, but still it's small in some sense. It just won't work for other examples. And so that's kind of where this got stuck. To my knowledge, no one ever followed up and even was able to do 3-dimensional real associative algebras instead. And so that technique doesn't generalize, and that's what one of my goals was in grad school, was to find some kind of method for understanding these shapes that would be more general, because understanding it the way that they did in that paper, they were able to identify like some pieces of this moduli space geometrically, but they couldn't do it for other variants of this problem. And especially, no such technique is realistically going to be able to do, like up here, when I have like an operation that takes 6 inputs and gives you an output, and I have some ridiculous equation that I want to hold for this thing, there's no reason to believe that type of approach that was done before should work on this. So, to my knowledge, there's no technique that will work in general, except possibly the thing that I'm going to be talking about in this talk that I'm preparing for. And now I haven't actually used what I'm proposing to understand these shapes yet, but I've done what may represent a first step to understanding them, because that's how it goes sometimes. So I did try one other thing from algebraic geometry, despite the fact that I didn't really find a lot of progress starting off with algebraic geometry with this problem. The other thing I tried was something called, I'm not sure if I'm going to spell this right since it's been a while, Grosvenor bases. I tried Grosvenor bases. So I used, maybe I'll post a link in the chat to this as well. So I've used the computer algebra system Sage Math, which is also, is also what I was talking about at the beginning of the stream, because this CoCalc is basically an online platform like Google Colab for originally I think it was made in order to do collaborative like work using that computer algebra system, the same way you'd use Google Colab to do collaborations with like stuff in Python or R or whatever. But Google Colab, to my knowledge, still doesn't support Sage. It's a free open source thing, and I think Google just doesn't have enough motivation economically to do that maybe. So I was using Sage Math, which was the original motivation, I think, for this collaborative system to be built. I was using Sage Math to try to understand these equations that I was getting, and so I was trying to have it compute these Grosvenor bases, which are like some kind of calculation that you can do for finding a simpler set of equations that describes the same set of points that you were interested in looking at. The problem is that although this is something that's a very like algorithmic thing, and you always can get an answer, you just run the computer long enough, what I found is that my simplest versions of these equations, like my simplest way of presenting these problems that I could find, it was too computationally intensive. Like my smallest possible examples were something that the computer had no realistic chance of actually working with. I just wasn't getting anything that was informative, and so this is also a thing that happens sometimes. Even when there's technically an algorithm for doing something, and it's been implemented, and you can plug it into the computer, even if you have a good computer, sometimes it just happens that this tool is not strong enough for the question that you're asking it, and it just won't give you a result that's useful, or it won't finish computing in your lifetime. It's just a fact of life sometimes that some parts of mathematics just cannot be approached by the tools that you have at your disposal at the moment, whether they're abstract things like algebraic geometry or concrete implementations of things related to that. Sometimes you just can't get it to work. Now, of course, it's possible. Again, as I said, I also haven't even tried to look at the problem this way in a long time. So maybe I'm better now, and maybe I would find something new that I didn't notice before, or maybe someone who's an expert in these things, in algebraic geometry that I have not really studied as much, would see something that I don't. But it seems at the moment like these tools, despite being very good for lots of other problems, just are not good for this. So I didn't have a lot of hope that it would be possible, and no one else has been able to figure it out either. So that's a reasonable question. Is there a merit to experimentally just kind of sampling the high dimensional space and trying to reduce the complexity and hint at the full shape? So I guess the short answer is yes, you can try to do things like that, and it will tell you something. But the long answer is that you're not going to. I think you're not going to. You're not going to get. How do I want to say this? If the goal is somehow understanding the components of the shape, what the basic pieces are or their dimensions, I think that it is not something that's going to be computationally feasible, because you're looking at objects in a very high dimensional space that you don't know what they are, and so you're going to necessarily do something that's an approximation. You're not going to probably do an exact calculation, because it would be really expensive. I mean, I guess you could. I mean, you could just use rational points. You could just take a point and say is the point 1/2, 1/10, 2/3, blah blah blah. Just take a rational point like that, and you could say does that solve my equation? If not, how far is it from that? And I could say oh, this wasn't really what I needed. This was off a little bit, but maybe a better guess would be, instead of 1/10, I'll do 2/10, and I'll leave everything else the same, right? And you could kind of proceed in this way and try to make progress towards the shape. Maybe the real shape is something like this. Your guess is over here, and you can make progress by varying the entries until you get here, until you land on the shape or close enough to say that you're on it. So that's actually some kind of I didn't put that in. So I mean, that's basically some kind of gradient descent. That's some kind of stochastic gradient descent that you could do to do that. And you could find points that were on the shape, or at least close enough to being on the shape. You could do that, and you could find a whole bunch of points that are on the shape. That's definitely possible. The problem is that knowing any finite amount of points that are on the shape is actually not super helpful. And if you don't only know that, if you did these rational points, it's possible that you would just go forever guessing and tweaking it a little bit, and you never actually get exactly on the surface. And then there are a lot of issues with this. Even if I knew, for instance, say I know that there's a one-dimensional shape that has these points on it, these 4 points. It's possible that the one-dimensional shape looks like this, it's, okay, pretend that that's like some smooth thing that's nice. It's possible that the shape looks like this, and maybe there's another one-dimensional piece that looks like that. That's possible. But the same set of points, could also maybe be points on this line and this line. And you might think, well, what if I did a lot of points, right? Like, what if I did like a billion, trillion, just a bajillion different points, and I found so many points on these things? The problem is that you can never say for sure, especially if you don't even know for sure that you have any points on the thing. You just know they're close. You can't say for sure what the actual shape is. And in addition to that, the expense of producing that computationally it's like exponentially huge. Like it's like an unattainable amount of computer resources to do this well, for whatever definition of well you would like to choose, because you're messing around not in two-dimensional space with one-dimensional curves, but in 8 or 27 or even higher dimensional space. You need like an exponentially larger amount of sample points to get something that's approximately right. And so this is related to like the problem of like you basically have what's sometimes called combinatorial explosion. It's not a real explosion, so you don't need to be afraid. But the amount of different parameters are so big, and the number of choices are so big that it becomes very difficult to explore. It's kind of like going from exploring your house to exploring like the Rocky Mountains or something. I can pretty much find whatever I need to inside of this house and in my home. Like, it might take me a little bit of time, but for the most part I can. But if you ask me to find, like, if you asked me to find a pen here, like a specific pen that was lost, I could probably do it. If you asked me to find a pen that was lost in the Rocky Mountains, I have no chance. I could spend the rest of my life trying to find it, and I wouldn't even be close. And so this is often a problem that happens when you're trying to computationally deal with high-dimensional space, is that you're looking for a pen in the Rocky Mountains. It's just like an unattainable vastness that you're exploring. And so, unfortunately, I'm not saying like you should never try, or like it wouldn't be a cool thing to try. It would, but unfortunately, messing around with this computationally is not maybe the most fruitful thing. Oh yeah, absolutely. There are no giant spiders in the Rocky Mountains though. Like this one's very tame, but I even just touched it a little bit and it's fine. It's just super chill. It's not dead though. Like I can tell. Like it's like it's just very peaceful. There's no giant spiders that will get you. If this thing's holding the pen though, I'm not going to try to take it because it probably wants it real bad. So I'm just going to leave it there. Okay, so thanks for the question. The question about trying to numerically approximate the shape. So I see. So you're hoping that you could show some region of the shape is relatively nicely shaped to determine a reasonable step size for sampling. This is a little far afield from what I was going to discuss, but it actually is related to some really interesting stuff that's related to machine learning and to artificial intelligence. Because I have a specific kind of higher dimensional shape that I'd like to learn, but often when people are trying to design systems that might be considered to be some form of artificial intelligence, often what you're doing is you're given a bunch of points in a high-dimensional space, and instead of thinking about them as real algebras, you're thinking about them as things like, maybe this is this represents like this person's like shopping habits, and this is this person's shopping habits, and you can think of those as being like points in a very high-dimensional space. Maybe I'll maybe I'll leave the details of how you can think of that, for another time. But that's kind of the idea. And you say, this is sitting inside of this is sitting inside of R 47 or something. But saying this stuff is in R47 or in 47-dimensional space isn't very useful. What we'd really like to do is generalize people's shopping practices so that we could find a predictable pattern that we could use to figure out, marketing, or, where to target. Maybe, if it was something medical, you could figure out what people's patterns of behavior were and try to figure out appropriate, treatments for different populations or whatever. There's lots of things you could do, but it basically always comes down to, you want to find some lower dimensional shapes. Maybe there's a line here, there's a sphere here. You want to find some lower dimensional shapes that all of these things live on. And so this is a common problem. And unfortunately, there's not really a good general solution to it. Mathematically, there are lots of reasons why there cannot really be a good, totally general purpose solution to the problem that I just described. I basically just drew pictures explaining why a minute ago, that these problems have a finite amount of data, but there's an endless amount of valid explanations of any such phenomenon. So in that sense, it's an impossible thing to actually give a definitive answer to. So we need to use more information than that, is basically the point. There's a question about is that principal component analysis? I am not sure if I've ever actually done that. I am aware of it enough to know that it's principal component analysis, but I'm not sure that I've ever actually. Yeah, I think that this is not something that I've ever actually done before. So I have the general impression that it is something useful, but unfortunately, it is not something that I already actually know about. So I can't say much about that. But yeah, I'd be interested to know what it is. I think that I've come across it in passing, but I think that unless I'm forgetting something that I've experienced, it's not something I've really done much. But I do at least apparently know that PCA is principal component analysis. But yeah. Now, see, if I was a little bit more unscrupulous, I would have just lied to you and given you some explanation of why you could or could not use it without telling you that it's not something I've done very much before. And believe it or not, people actually do that in math all the time. Of course, not anyone that I know, but yeah, that's a common thing. I see. Yeah, this is starting to sound. This does sound vaguely familiar, but I'm not going to pretend that I know how to do this. Of course, I know how to find a basis of eigenvectors, but the principal component analysis is not something that I can specifically recall having done before. The only thing I can imagine is that I may have done something computational where I used it and then forgot because I didn't actually do enough of it by hand. Maybe I was having the computer do it, but I don't specifically recall that. Although, okay, so you're saying you want the 2 or 3 eigenvectors with the greatest singular values, though. Okay, not the greatest eigenvalues. I imagine, though, that this is probably similar to how the eigenvectors that have the largest eigenvalues are the ones that really dominate when you apply a transformation over and over and over again. So yeah, that seems to be in a similar vein. Yeah, this is making me. I kind of vaguely feel like now that you're saying this, I kind of vaguely feel. Oh, buddy, are you okay? Oh, you're not spitting up. You're just Yeah, sorry. I don't think I can say much, and I don't think I can give much more detail without starting to actually read something. But this does sound familiar to me, but not familiar enough that I could give a whole lecture on it. But yeah, it's totally possible that something Oh, okay. I see. The singular values capture the greatest variance in the data. Apparently, yeah, that's again totally conceivable. I just I don't yeah, I'm not super familiar, so I cannot say at the moment. But thanks for bringing it up. Yeah, I mean it's possible that there's some other known technique that would be helpful, even numerically, but I just don't happen to know or have not have not tried. But I mean, it's not like this is a problem that tons of people have tried really hard, I think, to do. It's something that people have considered off and on for decades, and it seems like not a lot of progress has ever been made. So, I mean, it is conceivable that there's something that's doable, and we just, that's like a known thing that's doable, and we just haven't seen anyone do it yet. So, by all means, if you're interested, you might try. At least it might be a fun coding exercise. But yeah, thanks for the great comments though and questions. Oh, and I never did mention. I saw that there's the comment about the brown recluse spiders. Yeah, there are brown recluse spiders in the Rocky Mountains, but there's no giant spiders. They don't have to be. They don't have to be big to poison you. All right. Well, are there any other questions or things that people are wondering about other than this? Yeah, unfortunately, doing things numerically. I guess the summary of that story is doing things numerically in practice in like practical applications can be helpful, but it's still hard, and doing it for theoretical things is very, very hard. So I would like for there to be some more sophisticated, not to say that if something simpler happens to work, then I'm happy that it works, and I just didn't realize that. That'd be great. But maybe there's some more sophisticated way of understanding this. And so what I was working towards in the beginning was writing down equations that these structure constants would have to satisfy in order for this them to give an associative operation, in order for us to end up with an associative operation. And so I did this in a little more generality in the slides that I already wrote. And so so I ended up getting some equations like these, and maybe I'll show you how to get a specific one so that this isn't so mysterious. I'll show what it looks like in the specific case that we talked about. That's the paper, but yeah, let me show you how to actually get the equation. Oh, okay, that's a good question. How do I go from textbook exercises to this kind of work? Okay, it's a good question, but I think my answer is not going to be the most satisfactory answer, or maybe it will. I don't know. Okay, so I guess what I feel like I'm supposed to say, which is not what I'm actually going to say, is that you should try anticipating. You should try anticipating what the textbook is going to say that you're reading before it actually says it. Try to look at the title of the chapter or the section and guess what it's going to be talking about, or look at the statement of a theorem and see if you can prove it yourself before looking at the proof. And that's, you do that enough and you'll eventually start predicting things that weren't in the textbook, but maybe were in a paper, or eventually you'll predict things that weren't in anything at all. And I will say that there is an element of that I did throughout my education. However, the main way that I got to the point of doing this kind of work was actually by trying to do it when I was wildly not formally educated in order to do so. In other words, I tried to do stuff that, it was not exactly this, but stuff that was in the vicinity of this before I had taken an abstract algebra course, for instance, or topology, or whatever. And so I just kept trying to make new mathematical things that I thought was interesting. And of course I got better at it as I saw the things that other people had done and learned the math that other people had already developed. But I just was never really afraid of just kind of going off, like just half-cocked, like with no real plan or qualifications for whatever it was that I was going to do, and I just saw what would happen. And that's basically how I got to where I am today. So in particular, uh, when I was around 12 years old, I started messing around with division by zero. And so I just thought, like, what if I made a number that I thought, that I treated like 1 over 0? Like, maybe I don't know, I'll call it A. Just call everything little a, why not? It's the first letter of the alphabet. And so, maybe I'll just say that this is like 1 over 0. And what do I mean by that? I mean that, like, 0 times A is equal to 1, and it's also A times 0. And then I just tried to figure out if I could make an arithmetic that worked that way. But what I noticed was that, oh, hello there. We have someone new joining the chat. Hi. I'm talking about how I was 12 and I was trying to, do abstract algebra research before I really knew that much abstract algebra. And so I was like, oh, well, but if I do 0 times 0 times A like this, 0 times A is 1, so I get 0 times 1, and that's 0. But if I do 0 times 0 times A, then I'll just get 0 times A, which is supposed to be 1, but 0 is not equal to 1, and so this doesn't satisfy a familiar law of arithmetic. Oh no. And then I had said, well, it's fine, I guess, like I'll just say that you have to put in the parentheses. Why not? I'll just say that you've got to choose the parentheses, and that's basically just me saying, it's okay that it's not associative. And eventually when I got a little bit older, I was able to prove that if you define any such operation, okay, the proof is basically what I just wrote here, but I was able to see how this was really a proof that if you defined any such operation, I did have a specific example in mind. This isn't enough to define what it was that I was looking at. There was more detail. Like, I actually defined like an algebraic structure in the proper sense, although I didn't really know all of the abstract definitions of those things when I did it. I discovered, there's no system like this that can possibly be associative. I am more partial to clones than operads, but I'm cool with operads as well. But I'm a little more old school, Eventually I was able to realize that this was actually okay, and it's just that no such operation can be associative. But that's fine. That's just life, and life is okay. And I realized this, and that kind of got me interested in these non-associative algebraic structures and like generalizations of these things. But I did this before I ever took an abstract algebra course. Like, messing around with this type of thing is kind of why I like algebra, because being able to understand what was going on with this was very nice, and because it's a natural question. And it's a question that, furthermore, it's a question that no teacher that I had when I was that age, when I was a teenager, no one was able to give like a coherent, abstract answer to this question. It was just kind of like, you don't do this. And like the more detailed understanding of like, if you did something like this, it would have to be non-associative, and we don't care for that. That was not something that anyone showed me. That was something I figured out for myself. And that was worth so much. Like, figuring out anything like that for yourself is so valuable. It's not that you shouldn't let other people give you advice or teach you things. You should, but anything that you find on your own like that it's so much more helpful for your understanding, because you understand every part of what led to asking the question, to finding the answer. It's all you, and so that's what it feels like to generate new mathematics. So that was one of the first experiences that I had, and I've done other things like that throughout my progression, where I've asked questions that I might not have been equipped with the tools to answer, but I tried anyway, and I tried to find the tools, I tried to make them myself. Sometimes I failed, sometimes I succeeded, and that's really what it was. textbooks are not actually super similar to what it's like to actually do mathematics. It's really about that kind of open process of exploration of saying, what if I define this? What if I could make this kind of calculation or this kind of shape? Yeah. Oh yeah, and of course I definitely agree with the comment that it's a huge dopamine rush when you figure out something, even if later, years later, you say, this was trivial, this was simple. For you at 12 or 18 or 25 or whenever it was that was before for you, if it meant a lot then, like, that's important, Like, you always look back and say, I understood so little then, it was so obvious, but it was only obvious because you had that experience. Dobby, what's up, buddy? Are you having mathematical insights? No, he's just staring me down. Oh yeah. Yeah. So I have some other stuff to say about this. I appreciate the comment. I'm glad that my discussion of this was helpful. Yeah, I'm glad that my discussion of this was helpful, and yeah, I hope that you do have some things you can try or some things that you can explore. I do want to say something about time. Like, we all only have so much time. Even if we lived forever, there'd only be so much time, that we've experienced so far. Maybe I won't get into that, but you have a finite amount of resources that you can consume after any finite amount of time, and so we are limited in that way. And if your goal is to learn something well enough to become a professional at it, there is a big concern that messing around in this way is a waste of time because you're not learning as fast as you need to. And so I'd like to say, first of all, as long as you keep yourself grounded enough that your experiments are actually not just flights of fancy, but are things that actually have concrete answers. The questions are things that you can at least make some kind of progress on, and you get experience with doing that, then I think it's worth it. And I think that you'll learn a lot. I think that you'll learn a lot more by messing around than you will by trying to grind through exercises. I have done the grinding through exercises, but I've never read an entire textbook cover to cover, and I've never done every exercise in a textbook. I try to. I feel a compulsion to, even, but I always fall off. And when I really learn deeply, not just build some like basic skills, but when I really learn deeply is when I mess around like this and just find out what happens. So I do think it's valuable. But I also think, especially if you're not from an affluent background, if you haven't already made a lot of money in life, I think that it can feel especially scary to just mess around because you know that your time is very limited and there's consequences to failure. It's not like you're just gonna, have to go and like reinvest some of your money elsewhere or ask your family to support you for a while or something. If you're really dependent on yourself and you can't really expect anyone to guarantee you any survival if you fail, then doing mathematics in general, and especially doing it this way, can be very terrifying because it's not just a silly thing that you're messing around with anymore. It's something that, although it can feel like that sometimes, it's also critical to your survival. And that's one reason that I think it's so important to offer any kind of support that you can to people from disadvantaged backgrounds in math at any stage, because time is the safety to explore things like this is a luxury that those people don't have as much, and maybe I should say we don't have as much since I'm not from a particularly affluent background, yeah, I mean, it's worth it. It's still worth it. That's not to say that it's for everybody. It's maybe not for the faint of heart, but it is worth it to just mess around. Yeah, I mean, I wish that everyone could just feel free to explore whatever their curiosity was and learn that way, because I do think it's better. But even when you're in college, like taking algebra or topology, like you have to find a balance because you've got to be able to answer the questions that are going to be on the exam. But yeah, I don't know. So I guess that's all I have to say about that for the moment. But let's see. Oh yeah, good. Yeah, I see that somebody had a similar experience running down a rabbit hole when asked why is the unit of the why is the unit of area a square. Yeah, I think that's yeah, that can also be, yeah, that's the exact type of question that's like, try to answer something that you maybe at first would just say like, oh, it's obvious, or like you never thought about it, and like you can really find some cool stuff. Even if you can't answer your question, you often find some really cool stuff. Yeah, oh, and there was a comment about, struggling to add fractions at 12 instead of, doing all of this. But, I was thinking about adding fractions too. I was just thinking about like, if I was allowed to have 0 in the denominator, what is the proper, what is like the proper definition of like, what this is supposed to be? And I did actually come up with an answer. I don't think I have time to discuss it in this live stream, but I did come up with some kind of answer. Yeah, no. Oh yeah, it was Hartshorn. Hartshorn was what I started trying to learn algebraic geometry from, but I felt like it was not advancing the thing that I wanted to enough, and so I didn't stick with it. Maybe I would have had a very different perspective if I had, but I felt like I was just not getting the results that I wanted, and so it seemed like it was too risky. But you never know. So who knows? Maybe in the future someone who knows algebraic geometry better will take a look at this and they'll say, yeah, if you had stuck with it, you would have realized that you could do X, Y, and Z thing that I just don't know about. But I did come up with an answer, or at least a progress towards an answer for part of my thesis that was not algebraic geometry. Yeah. Well, actually, this always goes by so fast. There's like 10 minutes left in my scheduled time here. I really can't I can't believe it. I've had so much fun. It's been really cool like hearing everyone's questions. Are there any like last things that people want to hear about, want to say? I'm just blown away by how much interest there's been too, like on YouTube. Like I've been getting so many views. It's a little frustrating because I realized I wanted to make a new account that wasn't like my undergrad email account's YouTube channel, and so I'm trying to like get everyone from the old YouTube channel onto the new one, but people just keep subscribing to the old channel because like not everyone's gonna read like my message saying like you should subscribe to my new YouTube channel, but we'll get there. I'm getting close to I'm getting a more similar amount of followers on the new channel to what is on the old channel, so it'll be okay. But yeah, I mean, just let me know if you have any last questions or comments or anything. I always have so much fun, and I was correct that I did not actually finish making my slides, but that's okay because I have other time that I can finish making my slides. Oh yeah, thanks for the good luck on my talk. I'm very practiced on a lot of the general big picture stuff now because I talked to all of you about it, so that was really good. Let's see. Okay, so somebody's thought of making a study with me type thing as you catch up on papers. Please, by all means, do keep following and seeing where my channel goes. It is a relatively niche area, but I'm really pleased that a lot of people have been interested in checking out things that I've been up to, and I'll try to find different things to do every week, which I think shouldn't be hard because I have lots of little random questions and things that I've looked at over the years that I could probably keep doing one of these with a new topic for the rest of all time. Not sure about the dueling, but let's maybe make a rain check on that. I don't know if I'm ready to duel anyone. I did actually used to do math contests when I was a kid too, but I've fallen out of practice, and I think I'm probably not. I'm probably not. Even if it was a mathematical duel, I think I'm not necessarily going to be the fastest at solving a random Olympiad problem or something. Um, Although I'm sure I can do it eventually. Oh, and thanks. Yeah, thanks. Oh, I see. Yeah, so you could stream yourself spending hours to solve one problem and dumb it in foot, and that could, yeah, there could be a whole math streaming ecosystem. So now, actually, I do think that this is a good point, which is that like there are people who, are like pop science or even like pop math like personalities who make videos, or even like maybe there are some live streams, but I think a lot of it's more like things that were curated and designed intentionally to be like entertaining without actually requiring you to like do like it's not quite putting as much intellectual effort on the part of the viewer, so it can be consumed in a more casual way. Whereas this, although I do tell stories and there's digressions and like I hope is amusing. It seems like it is amusing to lots of people, even if you don't have all of the background. There's a certain intensity to this that I've been doing that's not there in those things. And I think that people actually live streaming themselves doing real stuff, whether that's real research or actually trying to learn something in real time, could definitely be really interesting, because that's actually like more similar to what it's like to be in a math department at a university, and you just come across people like working on the board, like trying to solve a problem or do their homework or whatever, and like you can talk to them about it or give a suggestion or whatever, and I think that that's really cool, and like I would love for people to do this online more. I mean, of course, for my own sake, I'd like to continue to be someone that people want to watch. But I definitely think that would be a great use of these tools. I think that's a great idea, is to be reading a paper, be doing some kind of exercise, and like I'd love to see that stuff. So yeah, please do let me know if you start doing something like that too, because I think that's really I really like this. I've been having a lot of fun with this, and I think it's a really good use of these resources. There's nothing wrong with watching people play video games or whatever. Like that's good fun. But like, I mean, there's no reason that this needs to be such a rarefied thing that like you can't access just hanging out with people who are doing math unless you're at some prestigious university. Like there's literally no reason for that in this day and age. Yeah, so for lots of social and political reasons, I agree that just the math streaming ecosystem is a good thing. It should definitely be a thing. I see there's a question about am I on some flavor of Linux? Yeah, so I am on Linux Mint, because I like Debian, whatever it is, but Ubuntu has too many ads, too much Amazon stuff. So Linux Mint is really the way to go. It feels like Windows XP sometimes with the interface, and I like that. 2025 will be the year of the Linux desktop. Any year now, it's going to happen. But yeah, that's cool. Actually, I shouldn't really give much of anything away because it's just starting. But I have a project that's going on now in symplectic geometry. So give it a year or two, and I might have some stuff to say to you about symplectic geometry. But it's cool that the journal application is written by a symplectic geometer. Oh no, I'm sorry. I think we're going to have to end the stream at this point. I definitely don't have time to get into whether it's what's going on with GNU and all of that type of thing. I think that's a little more than we have time for in the last little bit of the stream. Do you want to say bye, Dobby? Dobby, here, maybe Dobby wants to say goodbye. He seems like he's interested in saying goodbye. Dobby, come here. Come on, buddy. Yeah, well, thanks so much for joining us. It's been really cool. I'll have this up on YouTube soon, and make sure to stop by at the same time next week, and I'll do something else. Yeah, thanks so much. It's just been really awesome, and Dobby had a good time too. Yeah, it was really fantastic. All right. Well, yeah, thanks for joining. Thanks for watching. Yeah, bye everyone. This has been really cool. All right. Oh, I'm glad to hear it's reigniting your passion for math. Yes, that's what I'm here for. All right, it's definitely time. I am signing off now, but yeah, have a wonderful rest of your day or evening or wherever it is where you are.